All right, so I'm going to go ahead and start today. So we are in day 3 of a 4-day workshop on difference and differences. And I'm not going to do a thorough review, but I'm going to tell you what I'm going to tell you what we're going to do today. So let me go ahead and share my screen. Um, okay. And what am I doing? So here, mixtape sessions. For those that are just now joining, is the repository that we use for the for everything. And it contains here, just so you can see it, it contains all of our I think pretty much, I can't think of one that we've not stored here. So we've got basically all of the historic workshops that we've done, and we're moving into material here that is not actually going to cover the stuff that John does. John Roth at Brown is sort of a leader in this area, and a young econometrician. Ironically enough, he was Ariel Pecas's student, as well as Isaiah Andrews, a student at Harvard. So he's at Brown. He's done a lot of work on difference and differences, and Brantley Calloway has done a lot of work on differences and differences, and they've both kind of done frontier stuff. Like you can't use the word advanced and frontier. They're basically this should really just be John Roth's seminar on diff and diff, and this should be Brant Calloway's. And so some of it is material that we're going to cover. Most of it isn't. So I have a particular, I'm very different about how I teach this stuff. So we're going to be into slides, and essentially there are 3 differential timing slides I have in here. But I typically increasingly more and more, you can see here the last year, I increasingly am skipping stacking, but we're gonna see a little bit. So to kind of like big picture stepping back, what we've done, if I just could kind of like kind of a review of day 1 and day 2. I think the big picture would be like, what is difference in differences? Okay. And so I just to kind of summarize is first, it comes from the design tradition of causal inference, okay, where you don't really model the outcome so much as you take advantage of uh, naturally occurring variation in some treatment assignment, okay, uses longitudinal data on units, either repeated cross sections or panels, okay, and is fairly straightforward. So straightforward, in fact, that it's not really surprising that it was ignored by econometricians altogether. Okay. It was so straightforward that it almost defies being something econometricians would be interested in. Because here's all it is: 2 periods for a treatment and after a treatment, 2 groups, take a first difference after minus before in the outcomes for each group, then take a difference in those first differences, hence difference in differences. Okay. That's it. That's all it is. It is 4 averages and 3 subtractions. Okay. 4 averages and 3 subtractions. And that the assumption required for this to be an estimate of an average causal effect called the average treatment effect on the treated group, or ATT, is a few things. Number one, make sure that the baseline year or period for the treatment group is not treated, called no anticipation. 2, make sure that there is no interference between the treated units and the comparison units, called SUTVA. And some of what we're going to talk about today is kind of connected with that, that violation. Not exactly, but there's some of the violations of SUTVA are going to be very similar to what we're going to talk about with differential timing. And then lastly, with those two assumptions, there is only one additional assumption necessary. And it is that the post-treatment counterfactual average potential outcome of the treatment group of the treatment group's outcome of the treatment group's trend in outcomes is approximately the same as the actual realized outcome of its immediate comparison group. That's it. 3 things: no anticipation, SUTVA, and parallel trends. All of it really comes down to those 3 things. Every question that you typically have about difference and differences, every question that you have about differences and differences can really boil down to this. Are you, or rather, like, do you have longitudinal data? Do you have a treatment that is a dummy variable, that is a binary event? Do you have a treatment that happens to some units but not others? Do you observe them over time? When you are constructing your data set, do you have the data organized in such a way where the treatment group in the baseline is not yet treated? No anticipation could just as easily be called not yet treated, right? At baseline, right? That's like all it really is. This idea of like the treatment group not yet being treated in the baseline, making sure that the design elements of your data set are keeping the treatment group and the comparison group sufficiently distanced from one another such that whatever happened to the treatment group could not have interfered with the comparison group's life. Okay. All of these like design traditions, they're not really as much, if you kind of listen closely, they're not very statistical. They're very much connected with the way that an experimentalist thinks, right? Make your lab clean. Keep your bench clean. Keep it over here that the treatment group is not interfering with the comparison group. Keep them sufficiently set apart. But the problem is that with difference and differences, it's almost never the case that the treatment is randomly assigned, right? In the physical world of an RCT, physical meaning that the scientist or the data scientist or the economist or the social scientist, whoever, when they're running an RCT or an A/B test, they physically, there's no like modeling tricks that you're using. You're physically randomizing the interventions. And when you do that in the physical world of an RCT, the effects of randomization guarantee certain properties in the data that cannot be guaranteed, without randomization. And that creates some issues for a diff and diff study that are not there for an RCT A/B test. Namely, can you have confidence that the comparison group is the quote right comparison group? That's the biggest thing. Okay. In an RCT, the comparison group is always the right comparison group. It's always the right comparison group. In an RCT, the mean potential outcomes, the mean treatment effects, the mean covariates are in expectation in the infinitely large sample. Okay, there's still these like finite sample things, but in the infinitely large sample, identical. Okay, and they're going to be approximately fairly similar. It's going to get worse as the sample size gets smaller, but I mean, you know, in putting that aside, they're going to be comparable to one another. So that means that the comparison group's always the quote right one. Outside of the RCT, without randomization, you don't have that. You don't have that same level of confidence. And so a lot of people, when they kind of come to this outside of the experimental design tradition and they kind of go into the diff and diff, it can be like they bring a lot of baggage. People will typically bring a lot of baggage from their own statistical background to this kind of technique, and it'll be a couple of different things. No, homogeneous treatment effects are not assumed. They are not required. They are not a problem. The reason they are not a problem is because all of the heterogeneity is sort of like, how would you say this? It's like it's neutered. It's like it's not deleted. It's there, but the only thing you can really kind of recover easily with the RCT, at least in terms of the simple comparisons, are just the average treatment effects. Because all of the average potential outcomes are distributed the same, because the treatment group and the control group have the same distribution of their potential outcomes, and they have the same distribution of their covariates, and the same distribution of their unobservables. I mean, because it's so extreme like that, it's not that there's no heterogeneity. There could be all kinds of heterogeneity. It just doesn't create an issue, and it creates a little bit of a limitation because you're gonna be only really, I mean, it's not that you can't explore heterogeneous treatment effects within an RCT. You can. I don't mean that. I just mean that it's not going to pose a problem for your estimation of the average effects. It's, if anything, you know, you're in an RCT, there is no selection bias, and there is no difference between the average treated on the treated and the average treated on the untreated. And since those two things are usually the things that create issues for our estimators and our estimates. So there's not really an issue. But outside the RCT, without randomization, you don't have that same level of confidence, and you don't have it. You don't have it because outside of randomization, something else is driving the treatment assignment mechanism. Okay, something else is driving that treatment assignment mechanism. Treatment assignment mechanism. You always have to have a mechanism that is placing units into and out of an intervention. There's something that's doing it. Okay, and at the two polar ends of it is randomization. That's probably like, you know, the furthest edge to the right of a reason that a unit gets put into the treatment. They have no control over it, and it's being determined by chaos. Okay, some kind of, you know, truly unmodelable, you know, I'm thinking like, because I'm watching Three Body Problem. It's like this, you know, truly incapable of predicting why a unit gets into the treatment, and because it's being driven entirely by chance. So that kind of thing is at one end, and it has very special properties. And then at the other end is almost like deterministic things based on selection problems. Sorry. At the other end is a treatment assignment mechanism that is based purely on the potential outcomes. One end says the treatment assignment has nothing to do with the potential outcomes, and the other end says it only has to do with it. And those two are very different. And diff, when it works best, is in between the two. And because when you have that kind of extreme selection into the treatment based on the potential outcomes, it's not, it almost guarantees that you will not have, it almost guarantees that you will not have parallel trends. Okay. And so most of the time, we can't do anything. We can't do a whole lot about parallel trends violations except for a few things. One, we could address it with covariates, hoping that we have plausible parallel trends for treatment and comparison when we are making comparisons on observable characteristics. All right, so the two counties won't follow parallel trends unless we are comparing similar counties. And that is what covariates are doing for us. They aren't solving omitted variable bias. They are creating similar groups for which parallel trends we hope will be believable. I don't mean believable any change. You'd share these notes later. Yeah, I will definitely do that. I will put these here. That for which parallel trends we hope will be believable, that they aren't solving omitted variable bias. They're creating similar groups. It's covariates function for difference in differences, much more like what we are doing in synthetic control than most people probably understand. It's trying to create comparable groups for whom parallel trends holds when it doesn't hold otherwise. Okay, that's one thing we do. We can investigate the plausibility of parallel trends, but our tools are very limited. They're very limited. They are limited to basically two things: event study plots, checking the pre-treatment coefficients to be 0. Okay, that's one thing. But even that is not the same thing as parallel trends, because parallel trends is all about and only about the post-treatment parallel trends, not the pre-treatment. Just because you and your brother always wore the same clothes before you graduated high school doesn't mean after you graduated high school and one of you goes to one college and one of you goes to a different college, it doesn't mean that you would have continued to wear the same clothes. Okay? Doesn't mean that. In fact, you could have worn the same clothes every single day up until graduation and still not, after the event, have continued to had the event not happened. Okay? That's the thing. You have to always remember. It does tell you that this group is similar. And the more they're similar pre-treatment, it does feel like it's not crazy. It's not crazy to think that they would continue to be that way, but it's not the same thing. And then the other is the falsifications. Okay. Carefully thought through and carefully thought through falsifications can be just as useful, if not more so useful, than the event study in helping us believe parallel trends is probably true. Because what you get with falsifications, is more of an evaluation of the post-treatment omitted variable problem, whereas the event study tells you a lot about whether these two groups are on the same path. They're complementary, but they're not the same thing. And then the last is, you know, you might try something like triple differences. You might try something like John Roth's bounding methods. There's other things you can do, but that's kind of it. Okay. That's what we're going to look at. We're going to look at that. Okay, so Saban says, what about fixed effects? That's what we're going to do now. Is it similar to covariates? It is not really similar to covariates. And that's a good question. Fixed effects are variable. I mean, this is where things get kind of philosophical. They're not philosophical, but they're not what we think. Fixed effects is a variable. Covariates are a variable. So it's natural that you would think it's the same thing, and it's not the same thing. And we're going to see that in just a minute. Fixed effects transform the data. Covariates do too. You can see that in the Frischwald-Lovell theorem that they both are, quote, transforming variables in a multivariate regression. So that is true. In that sense, they are doing the same thing. They have to be doing the same thing because the calculations involved in putting in a dummy variable for whether you're an adult versus a dummy variable for your panel identifier, they have to be the same thing because they're both dummy variables. So they got to be the same thing. But the similarities between a covariate and a fixed effect can mask the differences. And in my opinion, the differences are a little bit bigger. So we're going to look at that now. Okay. So that's kind of where we've been. And then the last thing I would just kind of say is there's really conceptually two different ways of framing what a difference in differences estimator is doing. A lot of what I just said was about assumptions. Okay. A lot of what I was saying was about assumptions, parallel trends, etc. But I kind of alluded to something right here. Where is it? 4 averages, 3 subtractions, wherever it was here. 4 averages, 3 subtractions is an estimator. See below. Okay. There's basically conceptually 2 different ways of framing what a difference in difference estimator is. Okay. The first is my statement 4 averages and 3 subtractions. All right. That's literally taking 4 separate means of 2 groups and, running through that linear, calculation. Okay. And that will identify the ATT under no anticipation, SUTVA, and parallel trends. All right. And you can kind of just say, actually, the reason you can kind of, it's not exactly like this, but the reason you can say parallel trends is because when we look through what is inside the parallel trends assumption, it's got no anticipation in SUTVA. So you can sort of say like assuming parallel trends, and it sort of implies this because you can literally see inside the parallel trends expression, you can see no anticipation and you can see SUTVA, but I don't want to overstate that because it's helpful to kind of separate them. There's the 4 averages and 3 subtractions, and then there's something called outcome regression or imputation. And they are numerically identical. They are numerically identical without covariates. And I think they are basically probably under some situations, well, they are going to be identical also with covariates when you have strong support. I think that's probably going to be, I mean, I'm just kind of thinking out loud, but I think they start to kind of deviate a little bit when you don't have common support, because when you don't have common support, each of the methods sort of has a solution to that problem. And the 4 averages and 3 subtractions solutions use propensity scores, and outcome regression does not. Outcome regression will use prediction. And we're going to talk about that today. We talked about that with Heckman, Ickamer, and Todd. And then doubly robust does both of them. Doubly robust does both of them. So we're going to talk about that too also today, to kind of help square up, that as we're thinking about diff and diff, and we're thinking about these problems with diff and diff, we're thinking about these problems with diff and diff, you're going to notice that we're going to go down different paths. And in my experience, it's just helpful for people to kind of, because there's so much material in the workshop, it's as much as we can sort of, help group these things so that you don't just feel overwhelmed. One way to group them is just to kind of always break it down into, am I going to be taking 4 averages and 3 subtractions, or am I going to be doing imputation? And Imbens and Rubin said all of causal inference is imputation, but sometimes it's more explicit than others. So even this is imputation. Okay, it just uses parallel trends to do the imputation, but it's always imputation. But sometimes it's a technique that, sometimes it's a technique for doing the imputation that you really can't describe it in any other way than to just say, yes, I'm literally taking a model, estimating something in a first stage, and then taking those coefficients and then literally going in 2 steps. Whereas this is not exactly 2 steps, but hopefully that'll be clear today. So what I'll do is I will email you this. That's our kind of review of day 1 and day 2. And what we're going to do now is, we're going to go day 3 and we're going to go differential timing. Okay. And with differential timing, the thing that we're going to do is we're going to discuss the fixed effects estimator first with panel data. We're going to then move into the anomalies or pathologies of anomalies or pathologies of the fixed effects estimator when you have more than one treatment group timing date, i.e., one group gets treated in 2007, another group gets treated in 2010, another group gets treated in 2013, etc. Right? So we're going to look at that. We're going to see how 2A fixed effects performs in that situation. And then we're going to, because I said it's a pathology or it's an anomaly, we're going to talk about, resolving those pathologies, anomalies with different estimators that are either 4 averages and 3 subtraction style estimators like Callaway and Santana, Sun and Abraham, DeChase Martin and DeHoffel. I didn't spell that right. Or they are outcome regression estimators like Borisak et al., 2024, Gardner's two-stage diff and diff, or even Wooldridge's Moonlock estimator. I don't talk about all of these, but I don't talk about Wooldridge because these actually, the reason I don't talk about all of them is even going through these two can feel a little bit like overkill, and it kind of stinks. I mean, it does kind of, I've always feel very torn when I do these workshops because my desire is to give everybody credit and cover everybody's thing. But there's about six different estimators for differential timing, and they all kind of perform similarly. So it's kind of like a little bit overkill. But 4 averages, 3 subtractions, and even stacking is a version of this. Okay, it's an even version of this. So we'll talk about that, resolving those pathologies, and then that's it. Okay, that's it. And then day 4, we'll continue this and introduce the problems of interpreting two-way fixed effects with continuous treatments, and discuss a new paper. All right, a new paper. All right, so that's where we are. That took 30 minutes. Hopefully that sets us up kind of to get reoriented. And then what we're going to do now is we're going to do ATT GT. Okay, we're going to do the ATT GT one here today. All right, so let me go ahead and pull that up. And I'm not going to do this full, I'm not going to do this full history. I'll just kind of say though, that starting in 2018. Oh, good. Okay, thank you. I'm glad it was. So starting in 2018, the difference in differences literature really changed. I mean, John Cawley at Cornell, he told me something interesting. He said it's never been in his career the way it is now, where the speed from which when a new estimator appears in the timing from when an estimator appears, even in working paper form, to when it is required has never been a shorter time. Usually this stuff takes a long, long time. You think back, I mean, yeah, I'm not going to do it, but for instance, this one, they win the Nobel Prize for this. Embens and Angrist win the Nobel Prize for really all of their work in the 90s. They win it for, but Stockholm just really cites the 94 and the 96 paper on the local average treatment effect. I don't even have I couldn't even get Google Scholar to go back far enough, because I mean Angrist gets to Harvard in 89, Embens gets there in 90. They have a draft of the paper, I think by 91. And by that time, Angrist has left Harvard. He goes to Israel. And then the paper doesn't get published till 94. I say 95, but it's 94. So Embens gets denied tenure somewhere in this period of time here. He gets denied tenure at Harvard. I mean, I actually don't know how many Nobel laureates got denied tenure. I don't think it's a large number. He gets denied tenure. Look here. In 01, it's been cited 61 times. Okay, 61 times in 01. 10 years after, I think, a working paper was being circulated. Athey and Embens call synthetic control the most important innovation in causal inference of the last 2 decades. Synthetic control was developed by Alberto Abadi at MIT. He was a student of Josh Angrist. He's one of that first cohort of people. He wrote this paper with Javier Gardeazabal. Paper is published in 2003. In 2010, it's only got 85 cites in that year. It's been cited 5,300 times now. That's 5,300 times after 20 years of cites. Okay? Diff is its own animal. It's its own animal. It's wildly popular and only gotten more so. This paper by Borisak et al. Okay, I actually should, show this. So let's see, like I have to always go through. This is I just always can't always easily find the magnifying glass. So let's say Kirill Borisek. Kirill Borisek, 3,700 sites. Kirill graduated from Harvard. In 2016, he posts that working paper. Look at these sites of his total sites just exploding, 1,200. Where is it coming from? Two papers are driving it. The Borsak Hull Yarville paper on shift share in Restud, and this one. This one has twice as many. What is this one? This is the diff and diff paper. This diff and diff paper, I don't even have the full history here, but look at, in where does it start? 2017, 2016. I think I thought it was actually 2016. But anyway, so this paper here shows up at SSRN 2017. That year it gets 10 sites. Okay. And it really does, as I understand the history of it, it starts the whole thing. Because in the original paper, you have to go back to SSRN, go back to the very first. In the original paper, it's not yet finished. It kind of begins to document a lot of problems with the two-way fixed effects estimator. And ironically enough, Kirill and Xavier are graduate students at Harvard. They put the paper down because they're graduate students and they work in trade. As I understand it, they put the paper down to work on this paper. That's what they end up working on, is this paper instead. And as they put that paper down, there is a range of other papers that come in. The Chase Martin, let's say Clement, the Chase Martin, and I know I don't pronounce Clement's name correctly. Clement's paper, look at his sites. 5,400 sites. Young man. I mean, he's younger than, anybody younger than me, I'm going to call a young man. He's a very talented, extremely prolific, very, very, very excellent econometrician. Last year, 2,100 sites. Where is it coming from? Well, he's got a bunch of highly cited papers. Okay. But it's coming from diff and diff. So it's like fuzzy diff and diff with intertemporal fixed effects. I didn't realize that was his third most cited. That just came out. Two-way fixed effects, diff and diff survey, 500 sites, just came out last year, but this is the big one. This paper is the first paper that ends up getting okay, so this one came out first. Double fixed effects estimators with heterogeneous treatment effects. That one's first. Okay, I need to correct that, my memory. That one comes out first. And this is the paper that actually is the full tour de force of documenting all the problems with the two-way fixed effects estimator with diff and diff when you have heterogeneous treatment effects and resolving it. Another estimator that solves the issue. So you kind of go through all these things and you realize, it's like, it's so weird. 1,200 sites 3 years after the paper is published. Okay. Pedro Santana. Pedro. 4,200 sites. Huge jump. Although Pedro is, again, a very talented young econometrician. Look at the top papers. Diff and diff. Wait, so it goes diff and diff, 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 a diff and diff survey, but this is the big one. This is driving the train here. Last year alone, 1,800 sites of one paper. After it was published in 2021, in the year of publishing, 485, it's got 4,200 sites. Look back at Imbens and Angrist. Imbens and Angrist, when I collected this, the late paper only had 5,800. What is that at now? So look at this. This paper's got 4,200 after 3 years since it was published. Hito Imbens. This one, 6,500. It's going to pass that paper. It's going to pass that paper in a year. Because see, it's stable. And last year alone, he had 1,800 sites. And Callaway Santana is like the one that's becoming the more cited paper. So it's just like, kind of crazy. And there's all these. Andrew Goodman Bacon's paper, ends up being just incredibly influential. The Pedro Santana, the Sophie Sun, Sarah Abraham paper, Gardner, Wooldridge, John Roth, all of them. It's too many to name at this point, and they just keep going. And given the large number of citations, see, the large number of citations is probably not going to stop. These econometricians are like everybody else. They know that there is demand for this and there is tons of work to be done. And so there's just going to continue to be a lot of work done on the econometrics of diff and diff, probably for a while, partly because these are the leaders. Chase Martin and Dolful is the leader. Kirill Borsak and Xavier Yarvel, they're the leaders in this. Brant Callaway, Pedro Santana, they're very focused on all this material. Sophie has also diversified a little bit, but John Roth continues. So it's probably going to be a little bit more. So it's going to make it a little bit challenging for some of us who it's going to make it a little bit challenging because of the popularity of diff and diff amongst applied people, given this influx of a lot of econometrics on diff and diff. It's creating, something within this practice of applied econometrics that hasn't really been there. Thinking about what John Colley said, which was that usually it took so long for this material to kind of get adopted. It's never been the case, according to John, that it's been required so fast, which meant that all of us is kind of in this position where we're having to spend a lot more time. When you're a young person, you don't really quite recognize this. When you're a young person, you're learning everything all the time, because you're in graduate school, you're in econometrics, you're having to read all these papers. But you have to kind of trust me. As an older person, you sort of, as an older person, sorted into your applied work, and you were using the same tools a lot of the time. Most people were just using two-way fixed effects all the time, and they were focused on their topics. They were focused on minimum wages. They were focused on soda taxes. They were focused on these things, prime things. It's this very awkward thing that everybody is having to go back and just stay constantly tooled up, constantly teched up. Even for someone like me that's made it a career decision to stay as much as I can tooled up. It's a lot of work, so it's not really been like that for a lot of people. So that's all I wanted to say. Okay. So that's where we are. Okay. And so we want to talk about this two-way fixed effects, or what, actually, I thought that was kind of interesting that Clement called it here. What did he call it? The double fixed effects. That was kind of interesting. The double fixed effects. See, there was a time where you did not hear people use the word two-way fixed effects, not like normal people. When I was in graduate school, it was we just learned an estimator. Good. Okay, good. All right. I'm glad to hear that. So I was hoping that the old people, which other fields, definitely, well, Yinji says, do I have a sense of which fields? Within economics, every microeconomic field is having to learn this, because this graph is talking about economics, because it is NBER working papers, it is top fives. So the field, and this is all driven, diff and diff is all coming from what you would just roughly group together, applied micro. It means labor economics, public economics, education, development, health, public finance, law, crime. I mean, there's more probably. I can't even think of them all. less so industrial organization, not really that. Outside of economics, I mean, all I can go off of is anecdote, but causal inference has spread broadly now to really all. I mean, it's not that causal inference is not unique to economics. Like I've said before, causal inference goes back literally thousands of years. There's nothing unique about economics and causal inference. What's unique to economics and causal inference is the natural experiment tradition that came out of Princeton, merging with the work of Embens and Rubin at Harvard. That's the potential outcome stuff. The merging of that is this like avalanche movement paradigm shift. And that has been like imperialistically just rolling over all the fields gradually, and it gets, and then there's like lots of complicated interactions, but like that paradigm, where that paradigm of natural experiment causal inference has been influential is where all of this is getting ported in. Where there is no natural experiment potential outcomes based causal inference methodologies, this stuff probably is not going in. Okay, so like where that does not connect, probably you're not going to see diff and diff. That's my conjecture. And you're not going to see this revolution. Okay. But where it does, you will. So that's like, you have to kind of figure out where you fit in that for sure. Ronald, I'm watching you type and I'm curious what you're about to say. So diff and diff, though, comes out of that natural experiment blend of causal inference. And because of just I don't really know what exactly made it just a paradigm shifting thing for economics, but it was that is requiring revisiting our panel classes. Yeah, revisiting our panel econometrics classes. Yeah, the business fields. Well, it doesn't, when you, and this is all gets like the sociology of all this is really interesting. But I mean, Hito Embens, Susan Athey becomes chief economist at Microsoft in 2010 at the beginning of a wave of the hiring of PhD economists in tech. Initially, they really aren't there early on. They're not there. Hal Varian, Preston McAfee, they go to Google and they go to Yahoo. But they're really more micro theorists studying auctions and things like that. Susan is too. Susan wins the John Bates Clark Award for auctions and things like that. She goes to Microsoft. But that, once Amazon starts, it's like focused hiring, it's like spreads through. That's my reading of it. And that was really more empirical. That was more, the blend was moving away. That's my simplistic version of it. And now the modal hiring is empirical. Well, Susan is married to Hito Embens. They work on this machine learning causal inference stuff. And it just all starts to be more connecting it up to the business fields, going up with the business fields. And it doesn't, so you've got lots of things, basically lots of stuff pushing this into everything. Okay. It's not always the natural experiment stuff though. In the business fields, in the business parts, it's not always it can be causal inference and not the natural experiment stuff, because the natural experiment stuff has really been more traditionally the academics, Josh Angrist, Princeton. Hito has been more generally the econometrics. And that has been blending. Anyway, I'm kind of rambling, but anyway, so this two-way fixed effects thing, we've got to start. And at the start, it was used with diff and diff, because OLS, ordinary least squares, two-way fixed effects is a version of, two-way fixed effects is ordinary least squares. That's all it is. mean, that's not all it is, but that is what it is. It is ordinary least squares invented by Gauss in the 1700s or whatever it was. Okay, so it's not like some, it's not as novel or as different as you might think. Okay, and we knew that OLS, there was a particular ordinary least squares specification here. All right, there was a particular ordinary least squares specification that would identify the average treatment on the treated. This was this coefficient here, so long as you saturated, no covariates. Notice there's no covariates here. If you have a treatment indicator, meaning I am in the treatment group, not saying when I was treated, I'm just saying I am in the group that's going to get treated. This does not say when, and this does not say who. This just says it's the post-treatment period. And then this is the interaction. This says who and this says when. When you interact it and you have them by themselves, that's key, then that coefficient is equal to 4 averages and 3 subtractions. And under no anticipation, Sutva parallel trends, that coefficient will equal the average treatment on the treated. But you only had one group. You only had 2 groups, a treatment group and a comparison group. And you only had one post-treatment period. When it was a simple design, but it worked. Under parallel trends, it did work. Okay, working meaning it identified this right here was an interpretable causal effect. Okay, it's an interpretable causal effect. It can be, you look at that number, and it you can say that's a causal effect. It's a particular one. It's the average treatment on the treated. What's this one? Well, this one was used when you had, well, a couple of things. First of all, well, this one is used when you have a group of units that are treated. My first time to see this was what caused me to get into economics in the first place. My college degree was in literature. I went to the University of Tennessee, Knoxville, and my major was English or literature. And I basically really only focused towards the second half of the program, only focused on creative writing, poetry. That was my first, my dream from high school to the begin, like second year after graduating college. I was about 8 years. I was very committed to being an artist. That was my goal. My mom's an artist. She's a painter. My sister's a painter. My uncle who passed away, he was a painter. I don't have any painting, but I wanted to be a poet. That's what I wanted to be. And never took any econ, never took any stats, never really took any math. I took a pre-cal class that I failed my first semester because I quit going to all my classes and then had to retake it my final semester. Never took any, had no background. My first job was as a qualitative researcher down in New Orleans and doing focus groups. And I was reading the John M. Olin working paper series in the evenings. The John M. Olin working paper series was a John M. Olin Center. I don't even really know the full story of this thing, but like probably somewhere in here. Let's find it. A lot. There it is. Nope, that's not it. Oh, Becker. There it was. Nope, it's not even in here. So there was like, some of this stuff's not shown. So it looks like, but anyway, I found in this discussion paper series, I found two papers. One paper by Gary Becker, Nobel Prize speech. It's not empirical. Made me fall in love. I was like, that's it. I love economics and I want to be an economist. And then the second one was this paper, John Lott, David Mustard, concealed carry paper right here. There's like stuff was floating around everywhere. Here's the University of Chicago Law School, Coase-Sander working paper series, Law and Economics, right? And here we go. John M. Olin, Law and Economics, working paper series number 41. Crime deterrence, right to carry concealed handguns. David Mustard is a Gary Becker student at the University of Chicago. John Lott was doing some kind of postdoc or something there. And it's an empirical paper on deterrence, which was a topic that's associated with Gary Becker, who studied crime, among other things. He didn't even study crime. He wrote seminal papers on the theory, the economic theory that informs the economics of crime. And this is this paper that I see. It's the only one I really remember. The only papers I really remember reading that were empirical before I decided to go become an economist were this one and another one by John Lott, both of which were on deterrence. And here's what they say. Notice the word diff and diff. The word diff and diff is not going to appear in it. I'm not going to look it up. He says, using cross-sectional time series data. That's kind of jargony because it's not really panel data and it's not a repeated cross-section. It's a county level counts, aggregate total counts of crime. That's what Mustard had done. As a graduate student, David Mustard had pulled down the microfilm for the annual publications of the like Bureau of Justice Statistics. There's like 4,000 counties or something, 4,000 counties. He hand typed in every single county's crime rates for 8 different index crimes. That's the way back in the old days, that before people could get administrative data on crime, which is what they get now, they would use the Uniform Crime Reports. It was an annual publication, or it could even be monthly, annual publication of the crime. He counted them. And they did this model. I don't even know if the equation is in here. I mean, it's like actually like not the best etiquette because I think that it doesn't have it in here. But basically what they looked at was here's what they say. Using it, they got 77 to 92. This kind of data had not yet existed for analysis until Mustard did this. This is why I went to the University of Georgia. I only applied to 2 schools. One was the University of Georgia, one was Emory. And I went to Emory because I applied to Emory because they were using, a couple of people were studying capital punishment using these data. So I only applied to the schools where this stuff was being done. And they were basically doing fixed effects estimators of the effect of what? Concealed carry laws. Here we go. Right to carry concealed gun provisions. These were state adoptions of laws that allowed people to carry weapons on their bodies, but not show the weapon. Okay. And then they like study it and they're like, they're basically find that it led to a reduction. Do they say reduction? If those states which did not have it, this is not how I would word it, but basically they're finding that these laws led to 1,570 fewer murders, 4,000 fewer rapes, 60,000 fewer aggravated assaults from 77 to 92. Okay. How did they do it? It was a difference in differences model. It was a difference in differences. But notice the word, they don't say that. They don't say diff and diff. What do they say? They say repeated cross-section, time series, and I think if you go in here somewhere, it's going to say fixed effects. Okay? And that's what people would do. Okay? And that does this kind of like, because basically there's 2 kind of rivers in this program evaluation. One river is the diff and diff river. Okay, it's very explicit about, 4 averages, 3 subtractions, comes out of Princeton, Harvard, MIT kind of groups of people. And at the exact same time, there's like a more traditional panel group of writers. Okay, they're using the same tools. But this group's going to say, well, they're using the same tools. All right. But what we're going to see is that this right here, because it uses multiple treatment groups, ends up having issues. Not that this paper has issues. I'm not saying that. I'm saying the method has issues that are not present. Those issues are not present when you have one treatment group and one post-treatment period. This will always, quote, work. Under no anticipation suit for parallel trends, you don't even need covariates. You don't need anything else. This will equal the ATT, and this may not equal the ATT if you have more than one treatment group. Okay, so that's what we're gonna do. We're gonna now look at. We're gonna take a break, and that was like 1 hour of stuff. So we're gonna look now at this two-way fixed effects estimator. It's the workhorse estimator in program evaluation. Historically, it was the workhorse estimator in what you would just call, for lack of a better word, program evaluation kind of work, studying laws. Okay, definitely very popular in law and economics. Okay, and it was adopted for difference in difference designs. And it was adopted when treatments were adopted at different points in time. And there was nothing wrong with that, because we're going to show that this right here, that coefficient with the fixed effects estimator, where those are dummies for years or periods, and those are dummies for the panel units, states, persons, firms, whatever, schools, that will be unbiased. That will be an unbiased estimate of a parameter. Okay. It'll be an unbiased estimate of a parameter, which is what you're looking for. Okay. So it gets adopted, but we're going to look at what makes it unbiased. And it's not always super transparent. It's easy to implement. That estimator is easy to implement. It takes 1 second, and any kind of standard, the larger the data set, the more units there are, the number of fixed effects can be very large, but there's packages that'll make it go very fast. Even then, easy to implement. And not only that, it handles time varying treatments really well. Has a relatively straightforward interpretation under constant treatment effects. But turns out its interpretation is complicated with heterogeneous treatment effects, which is why DeChase Martin called it, he says that, two-way fixed effects with heterogeneous treatment effects. So that's what we're going to do. We're going to take a break, come back in 15 minutes. We'll come back at 18 minutes on the hour, and we'll be ready. We'll come right back. Right. So see you guys in a second on the track here. Doesn't make the noise anymore when I start recording. I used to. Okay. So two-way fixed effects. We have panel data follows the same units over time. All right. And that would be what this is too. Using cross-sectional time series data for US counties. It's the county is the panel unit. It follows it from 77 to 92, and it is not a sample of crime. Okay, it's not like a 5% sample of crime. It's all the crime. It's actually not all the crime, because it requires a police department to participate in the Uniform Crime Reports program that the FBI does, but they have very high compliance or participation. So there is a lot of it, but it's like, meant to be a count. Uniform Crime Reports, it's meant to be a total count of the crimes, right? Versus a repeated cross-section. And the repeated cross-section is a sample. That would be basically everything here at IPUMS. All these are survey data, census survey data, current population survey, monthly surveys. Census is a survey. Time use survey, health survey, all these things, right? So these are surveys, and surveys sample. They are not everybody. They sample, and they have these potential issues that you have to address that we talked about, where maybe the composition of the panel unit is changing. Here it would be like a county is changing because you're not following the same people, right? So they're kind of like, there's all these little issues. Nevertheless, diff and diff can be used with both of them. It works with both of them. All right. But panel estimators technically are about the first, because you cannot have in a repeated cross section, if the unit of the observation, it's all about the unit of the observation. If the unit of the observation cannot be observed in every period, it is technically not a panel. It is a repeated cross section, because it just means that, yes, you can observe the county over time, but if the county is a sample of individual people, okay, and the unit of observation is the individual people, then you can't put in a fixed effect for the person. You can't put in a fixed effect for the person. You can put a fixed effect for the county, but not the person. So, it's all about what is the level of observation that you're working with that makes it whether or not it's going to become a panel, unit, but it also has to do with the sampling. It's both of them. So panel estimators estimate causal effects in situations where there are unobserved factors associated with the treatment and with the outcome that create these endogeneity problems, right? So but it's a particular kind. It was developed, as I understand it, it was developed in order to solve a particular kind of endogeneity problem. It does not solve all of them. It solves a particular kind. And in some ways, the problems that it solves, that two-way fixed effect solves, are probably not the problem that you have. That's my personal opinion. Because the problem that it solves is that you have a confounder, okay? You've got some confounder that is associated with the treatment variable, and which causes the outcome, causing the treatment coefficient, the treatment variable, to become endogenous. All right. Because it's correlated with the error term now. But you're going to assume that whatever that confounder is, that it doesn't change over time. That's the whole trick of two-way fixed effects. Most people think of two-way fixed effects as just the dummy variables. That's what they think. They think to themselves, oh, two-way fixed effects is putting in the dummies. And it is. Okay, we're going to see more about it. But it solves a problem if and only if the unobservable at that level of the dummy doesn't change over time, because you're going to see that when it doesn't change over time, then the dummies eliminate the confounder through a demeaning of the data. That's what the fixed effects do. The algebra of it demeans the data while retaining the identification of the treatment parameter, so long as you assume constant treatment effects. Heterogeneous treatment effects make that all screwed up. Okay, so but originally the fixed effects estimator doesn't even have, potential outcomes, and it doesn't have heterogeneous treatment effects. If you look back at your notes in your old panel econometrics notes, you'll notice what I'm talking about, which is there's no subscript on the delta. Right? There's no subscript. There's no I subscript. What does that mean? That means everybody's got the same treatment effect. Okay? Constant treatment effects. When there are subscripts, means everybody has different treatment effects. But rarely do you model that in that. And what you hope, what people would hope that came from that experimental design tradition, that came from that like Princeton, Harvard, MIT tradition. You saw this with David Otter's, like on the first day, David Otter kind of describing this one two-way fixed effects estimator that he had done. He said, he basically says, well, under constant treatment effects, that'll be an average treatment effect. Well, people like Lott and Mustard, the word treatment effect's not even going to appear in this paper, because it doesn't come out of that, like that background. So heterogeneous treatment effects almost like are not relevant really at all. They're not really relevant at all in the history of that panel stuff, because even the word treatment effect does not ever get mentioned. I don't know if I make too much of this stuff. I don't really know if this is kind of like this obsession that I have with these whole like people with different paradigms who seem to be using the same things and like don't speak the same language, but they think they use the same language or they use the same words. That's like, you know, my obsession with all this, apart from the actual tools, is like, you know, because I'm just going to say this one real quickly, briefly. At the University of Georgia, mustard was taught me labor, and there was not a single time at the University of Georgia that I heard the word treatment effect, that I heard the word causality or causal inference. Not one time. And my field, the field that I specialized in, was econometrics. And I never one time heard it. I had a very traditional, for lack of a better word, econometrics training by econometricians who did not come from a lineage of Hito Imbens, Don Rubin, Josh Angrist, Orly Ashenfelter, David Card, any of that. Didn't have it. So when I go out on the job market, it was really here, you know, it was this material that really hit me because I had a panel paper. My job market paper was a panel paper. It was a quantile regression panel paper. And, but, you know, really did not think in terms of natural experiments. My job market paper did kind of have that a little bit, but it was very much driven by the question and not so much a natural experiment. And I would be talking to people. And I remember talking to my colleague, Mark Hoekstra, when he was on the market too, because like he graduated in 06, I graduated in 07. We both kind of came from lower ranked schools. Like I came from Georgia, he came from Florida. But we might as well have come from like Mars and Venus in my mind, because Mark's professor was David Filio, who went to Wisconsin, or maybe it was Northwestern. You know, and like that's a department that had a lot, their labor group, they're very structural there, but they also could get, you did learn it, you know. At Georgia, it was like, you know, David Mustard, he's not like a natural experiment guy. He's not like a natural experiment guy. He's a Becker student, uses traditional econometric methods. Chris Cornwell, my main advisor, panel econometrician, Scott Atkinson, Ron Warren, none of my professors talked this way. Even when they came from labor, labor is a very big tent. Okay, there's lots of people with lots of different backgrounds. Orly Ashenfelter is not the only labor economist, you know, like in the font of it. So like, you know, so for me, this stuff was like so confusing. This was so confusing how it could be that I was talking to people and we were like talking past each other. So this is what you are assuming in two-way fixed effects. You've got this unobserved unit level. I is the unit. It's the panel unit. Let's say it's a person. Okay. Person. Some unobserved heterogeneity. All right. Meaning it is something unobserved that doesn't change over time. Notice that there's no T on it. Doesn't change over time, but it's fixed. If it doesn't change over time, it's fixed. It's a random variable, but it's random across the population, but then it gets stuck. So it would be like randomly assign IQ, randomly assign conscientiousness, grit, you know, emotional intelligence, or a physical characteristic, race, or something like that. That would be like a physical trait or something that's not malleable. It's not malleable. It won't change. It won't change. Notice that the treatment cannot cause the unobserved thing. There are no arrows going from the treatment to the person, okay? And it's unobserved, but it's apparent. Look, it's apparent. It's an ancestor to the treatment variable. Maybe if it's like, you know, IQ, maybe the treatment variable is going to college. Or if it's grit, maybe it's about going to college or completing college. Notice here, it's like, you know, it's a Z, you know, I'm not in college. I'm not in college. I've completed college. Okay. And what causes it? Well, maybe some variables that don't change by the person cause it. And these are observed, right? They've got a solid line, and these are unobserved. They've got a solid line, right? That's usually the way we think about all this stuff, is like covariates, whether observed or unobserved, are driving the decision making. and then the rest of it's random. I mean, that's like, that might as well be the simplest way of thinking of things in a regression. It's like there's observed stuff, there's unobserved stuff, and there's random noise. Those are the three ways that econometricians usually tell us that we can practically like use the real world. And it causes the outcome. All right. This is sort of the DAG, the directed cyclic graph that shows when you can use two-way fixed effects, sort of. All right. And there was more to it than this, but it would be like you could use it, but notice what you couldn't have. You could have the treatment cause the treatment in the future periods. That's fine. But you could not have the outcome cause the treatment in the future period. That is prohibited. The outcome cannot cause the treatment, right? So you can't have that. Nor can the covariates be endogenous to the treatment. So there's all these limitations on when it can be used. So it was traditionally used for estimating constant treatment effects with unobserved time invariant heterogeneity. It's a linear model. If it's linear, you're going to be estimating averages. You're going to be estimating conditional mean treatment effects. If you want the median, you have to use quantile regression, right? So if you care about averages, you can use linear regression models. If you want quantiles, you can't, okay? And when you enter into the world with these dynamic treatment effects and differential timing, the standard specifications that we're going to talk about, they get perverse. So when do you not use it? You don't use it if you have simultaneity. Okay, so if you're interested in estimating the elasticity of demand, all right, the elasticity of demand, or if you've got like a situation like what even be more specific than that. So if you've got like this kind of situation, price, quantity. One of the most, like when I do kind of like office hours with firms, like, one of the most common things that firms really want to know is they want to know a demand elasticity. You know the demand elasticity, then you know how to set your prices and you can make predictions about, revenue and these very important things, right? You know the demand elasticity. What is the demand elasticity? The demand elasticity is this. This is demand elasticity. It's E, and it's the change in Q divided by, or log Q, change in log price, right? Now you can get that number, right? That's a little bit misleading, actually. That is not actually what it is. That is how it is calculated. No doubt. That is how it's calculated. But you can get biased estimates of the elasticity by doing that calculation. Like this, you could go log Q, regressed onto a coefficient plus, log P plus a bunch of covariates plus error. And you can get, the coefficient on log P will be change in log, that is the expression, is the calculation for elasticities. But it isn't an elasticity unless it is moving up the demand curve. Okay? So that means that you've got to have, in order to get an elasticity, you got to have an instrument. That's the only way you can get an elasticity. So you got to have something that shifts the supply curve. You cannot run this regression unless you can instrument for price. You need something that will shift the supply curve. Well, that's another way of saying reverse causality. You've got stuff that you've got quantity being determined by price. You got price being determined by quantity. They're both being determined by a system. All right. So you can't use fixed effects. You cannot use fixed effects unless you can satisfy something called strict exogeneity. And strict exogeneity is this right here. The average of the error term in all periods for all conditional on all of the x's is 0. It means that the error term, which is always, the error term is a regression concept. The error term is independent of all the x's and all periods, okay? And it's independent of the c, right? It's called strict exogeneity. And that is, oddly enough, violated in a situation like this, which you wouldn't think, like, what would that have to do with it? But, you'd be surprised. You would be surprised how many firms want to just run that regression, or they just want to run this regression and the mean of it's this, the unobserved heterogeneity. That would be like anything unobserved. We're going to get into that, Rock. We're going to get into that. So you cannot estimate an elasticity of demand just using a simple regression. It doesn't matter how many controls you put in there. It's going to violate. It is absolutely going to violate strict exogeneity. Will not stop someone. That will not stop someone out there from doing it, but it won't work. Even if it spits out a number, that does not mean that it's true, right? So you need strict exogeneity, okay? And strict exogeneity actually is a very pregnant concept. We're going to get into it. So time varying unobserved heterogeneity will also violate it. You cannot have C has to be fixed over time. The unobserved factors that are determining whether or not a person adopts the treatment and determines the outcome, whatever it is, that's fine. Two-way fixed effects can handle it so long as it doesn't change over time. Okay. So here's the notation, right? So we're going to let Y and X. X is going to be observable random variables. C is going to be unobservable, an unobservable random variable. And what we're going to be interested in is the partial effects of a particular random variable, X, we'll call it XJ, in a regression, population regression function, right? Not working with the sample at the level of the population. We want to know what's the mean of Y conditional on X, where this is a random, this is itself that's going to be a random variable. And we're going to imagine the mean of Y conditional on this means that I can imagine changing these values and then having the mean change, okay? So we're going to observe a sample of I in cross-sectional units, okay, to estimate this conditional expectation, right? X is going to be a vector, a 1 by K vector. X is just covariates. It's like, the firms, I don't know, firms, number of employees or something. It's all these things about the firm, or it's the individual. Okay. For each unit, though, unit is a person, a firm, a panel unit. For each unit, we're going to say there's all these covariates and there's all these outcomes in each period. Why? This is all the data that we have. The only data that we're going to have in this data set are outcomes and covariates and treatment variables. We're not going to have data on C, but we're going to have this like cross-sectional unit. They're going to be drawn from some population, and you're going to end up with the outcomes here. What am I doing? So here we're going to be interested. Well, we'll get to this in a second, right? So we're just going to have a sample of data, all right? And there's going to be 2 observable concepts, but 3 total concepts. Okay, so there's going to have outcome per unit per time, variables per unit per time, and those are going to be in the data. And then this one right here will not be in the data. And this is the Rock. He said, what is it exactly? I like to think of it as the easiest thing for me, because I'm an applied microeconomist and I typically work with individuals. I typically think of it as IQ. I think of it as IQ because I'm usually a labor economist estimating the returns to education on wages. And in that problem, when people are estimating the returns to education on wages, they're always worried about C. What is C? IQ. Unobserved ability that varies by person. Okay. Yeah, probably, Anna. I need to think about that. I'm not exactly sure how that violates this, but that sounds like I'm not sure. Let me think about it, Anna. I'm not positive. No longer eligible. As long as you're still treated, do you move out of the treatment? You're treated, then you move out of the treatment. That does not necessarily violate it. The turning on and off of the treatment is not necessarily a problem. Um, but let me think about that some more. So usually what happens is that you don't always represent it this way. You'll represent it in matrix notation. So it'll stack it. So you have a single unit that gets stacked. In fact, like this is Anna in 2020. This is Anna 2021. This is Anna 2022. This is Anna. Okay. And so, like, all 71 of us have an I. There's 71 of us, and we observe all 71 of us over time. And these are all of our covariates. This is a matrix of each individual's covariates, and we're observing those covariates over time. They could be changing covariates. Okay. And then we can stack them. And we stack them like this. This is Anna. Okay. This is Rock. This is me. So it's like you have all of them stacked into one stacked matrix representation. Same thing over here. So we're going to look at everything's going to be kind of expressed in terms of the matrix. So here's the expression. Ignore all this stuff, but like, because I think I've not really enjoyed this slide very much. But unobserved heterogeneity. So this is like for a random unit in the data. I'm going to say Anna. This is like Anna, person I, 2024. Anna's Y's, her outcomes, are based on what? Three things. The covariates in the model, which are, all of these, right? It's like Anna's age, Anna's sex, Anna's like, parents, education, parental income, all that stuff. And then like Anna's, and maybe this right here is our variable of interest, Anna's education. Oh, are you leaving the same? Okay, I'll let Reese respond to that. All right, so that's one thing that determines it. Another thing that determines it is that unobservability, how smart Anna is, how much conscientiousness she has, how much grit she has, how much emotional intelligence she has, all that kind of stuff. Okay. Now there's some things like that that are fixed over time. So some of that stuff may not be. You go to therapy, you can deal with things that you think are fixed that aren't fixed. Okay. So like cognitive behavior. But then there's other things that are fixed. All right. So like, your race is fixed. There's other stuff. Okay. So this is fixed over time. There are unobserved factors though that are not fixed over time, that are unobserved. Your social network. Okay. Your social network is unique to an individual and it is not observed and it changes over time. Okay. And it might be related to X and it might be related to Y. Well, that's going to screw everything up. And time varying unobserved heterogeneity, I mean, is pretty brutal. You're going to need an instrument. Time varying unobserved heterogeneity, you're going to need an instrument. Diff and diff is not going to help you. Okay. So then you got the error. Error is all the unobserved factors. Okay. That would be, this is where the social network would be. Unobserved factors. Okay. It's sometimes called the idiosyncratic error. In order for this regression to work, okay, we have to make assumptions about the unobservables. All right. When we ignore the panel structure, well, we've pulled it out of the error term. It is going to be in the error term, Ollie, but like what we're going to show is that let's imagine that there is a time invariant and time varying unobservable. We have like basically two types of unobservables. And this one is out. So let's say that like we have this composite, they'll usually call it a composite error term. And if I ignore the panel part of it and I just regress y onto x, and I say, I'm not even gonna take advantage of the panel. Okay. Then it's as though you have, well, it's not even as though you now have to say, I have this error term, not this error term. Okay. What is this error term? It is the sum of both of them. It's the sum of Anna's emotional intelligence and her time specific unobservables, her social network, right? Her emotional intelligence, which doesn't change over time, and her social network, which changes over time. Okay. Well, so what happens? What happens when I regress y on x, but x is correlated with c, meaning Anna's emotional intelligence is correlated with her completing college. All right. Then then you can see what happens. All right. Well, if that happens, if C is correlated with X and I don't do anything, yes, I have omitted variable bias, and X is correlated with the error. And when X is correlated with the error, that coefficient will not be an unbiased estimate of the true parameter. So we need to eliminate it. How do we eliminate it? All right. Well, so there's, first of all, one way to eliminate it. Yes, we're not going to do first differencing. We're going to only do the fixed effects because we're so focused on the diff and diff stuff. But in these panel classes that you'll take, you'll learn all the ways of kind of addressing it. First differencing, fixed effects, random effects is not exactly a way of addressing it, but these are like, there's a whole family of panel estimators that are like focused on, how are we going to survive this situation? Okay. And one of them, it says, well, pretend it's not there. That's your standard approach. Pooled ordinary least squared. Pooled ordinary least squares will allow you, running this regression can let you get an unbiased estimate of that coefficient if you assume that the unobserved heterogeneity is not correlated with X, which means that's not what we said here. But like we said, if you do assume that it's not there, that the reasons that Anna completes college has nothing to do with her social network and has nothing to do with her emotional intelligence, that they're independent of one another, then you can run this regression. And it's called pooled ordinary least squares. Okay. And it means her education it means that V is strictly exogenous. That's a slightly different thing that I did over here. I said the error term, strictly exogenous. But now I'm saying, well, if you're going to ignore the panel structure, then you have to basically make that assumption. You have to assume that this right here is called strict exogeneity. Means the composite error term in each time period is uncorrelated. And it's actually stronger than that. It's independent, not uncorrelated, but independent. Independence gives you a lack of correlation, but lack of correlation is not the only, it goes in the other order, but let's just say that for now. Uncorrelated or independent with the past, current, future regressors. Okay. If, though, that is not true, if the reason, or at least part of the reason, doesn't have to be the only reason. There could be like a bunch of reasons, but if one of the reasons that people, not just Anna, but like everybody, if one of the reasons they finish college is because of their emotional intelligence, all right, then pooled ordinary least squares will not give you an unbiased estimate of the treatment effect. And then you have this other thing, if the V's are serial correlated, then also the standard errors will be wrong. Right? So the thing you're always, in these panel methods, you're always asking is, well, is there a time constant, unobserved variable that is correlated with the regressors? It's awkward to phrase it that way sometimes, but if there is, then pooled OLS is going to be problematic, which takes us into fixed effects. And I'm just going to kind of move more quickly into fixed effects. All right. When you do OLS with fixed effects, okay, that phrase fixed effects, what are you doing? You are including, and I should say N-1, N-1 individual dummies for every single every single person, all right? Except for one, because you can't put in all the dummies. So you have to leave one out. And when you do that, though the coefficients on those dummies have to be estimated. Those parameters on those dummies have to be estimated, as do the coefficients on the variables, right? And so there's a minimization of the sum of squared residuals in that panel context. When you put in those dummies, you get coefficients on every dummy, and you get coefficients on every X, okay? The coefficients are the fixed effects. The dummies, rather, are the fixed effects. And what does it do? It transforms the data. All right, I'm going to skip to this here just because we're running out of time, but the first order conditions for this minimization turn out to be deviations from those fixed effects, turn out to be deviations from the mean. They're not first differences. They are in this coefficient here, this beta hat on the covariate of interest. Let's say it's education or amount of schooling. What is the beta hat? It's a transformation of schooling for every single person in the data. You take Anna's schooling in all years of the panel. So it's like, say it's 5 years of data. It's like 2 years before, so I say it's 10 years of data. And we've got her a couple of years before she started college, and then a couple of years after. And then we have everybody. Some people never go to college. Some people are always in college. All right. We got all this variation in the X. All right. When you put in the dummies for every person, what it is doing to the data is this. It takes the average schooling for Anna. Okay. It takes the average schooling over the 10-year period of time. Yes, sometimes she has no college and sometimes she does. But for the panel, what's the average number of years of schooling? So say the average of the dummy variable schooling or of college, the average of it, say, is 0.4, because like maybe 40% of the time, it's, of the 10 years, only at the very end for the last 4 years is that she college educated. The rest of the time she was not. So we had 0 plus, we added all those numbers together, took an average over 10, it was a 0.4. So that's the mean. Every single person has a mean of the X, okay? You then subtract. I mean, you don't do it. This is what OLS is doing. It's as though it's doing it, or not even as though it is doing it. It then takes from every single year of the panel, that 0 or 1 in this case, and subtracts out a 0.4. So sometimes it's a negative. It ends up being a negative. It's called, usually the way you would learn it is X dot dot. That's what I would always call it in panel, X dot dot. Because the expression of solving for, the OLS estimator is X prime X inverse X prime Y. So but it was a transformation. It would be X dot dot inverse X dot dot prime. And then you would also do the same thing to the outcome. You would demean the outcome, and you would run a regression on the demeaned variables. Well, look what that does. Why is that so special? So here is Anna's outcome in every single period. This is Anna's, earnings in every single period. And it's based on how much schooling she has, and it's based on her emotional intelligence, and it's based on her social network. Okay. I then take the average. Okay. I take the average of the whole equation. This is her average earnings over the whole time period. This is her average amount of schooling over the whole time period. This is her average emotional intelligence over the same time period. I don't put a bar there because it's the exact same. It's the exact same. Her average emotional intelligence is a 95. In every period, it's a 95. The average of a 95 over 10 periods is a 95. So it's still the same thing. This is her average social network over the time period. I then demean. Why? Because that's what it's doing. That's what it's doing. When you put in those dummies, it's demeaning. There it is right there. Demeaning. But since it's demeaning, it's also demeaning it to the right-hand side. So we demean everything. at her schooling minus her college education dummy variable in each period minus the average of college over the whole panel plus a 95 for Anna minus a 95. Well, that's a 0. And notice what it did. Through the demeaning process, it deleted. Through the demeaning process, it deleted the unobserved heterogeneity, and then it ran a regression on it. It's a simple trick. It's a trick that works if that doesn't change over time. That's it. It's an assumption about the confounder. It's an assumption about the confounder. It says the confounder is heterogeneous to all groups of people, but it doesn't change over time, but it is a confounder. And if it is a confounder that doesn't change over time, then through the inclusion of the fixed effects, it deletes it. And now you can just run a regression on this. And now you just need strict exogeneity. You need strict exogeneity here, that the error dot dot is independent of the x dot dot, which is called strict exogeneity. That's what it was. All right. Strict exogeneity, since this error dot dot is what? Error in every period, social network in every period, and it's the average. See, so it's now you need for this method to work, you need the social network for Anna to be independent in every period of education in every period. They have to be, and has to be independent of the conditional on C. And there's 3 ways we can do it. And this part right here just means there's variation in the x dot dot. Okay. So how do we do this practically? 3 ways. You could run a regression. You could run a regression of the demeaned variables. You could literally go in and manually demean it. Manually demean it. Right? And I'm going to show you that. Run a regression on the demeaned. You could run a regression of y onto x and then not demean, but put in dummy variables for every single unit. Or you could use a canned fixed effects package. In R, there's the great one is Fixest, F-I-X-E-S-T. In Stata, it's the high dimensional fixed effects regression, AREG, XTREG. There's been a bunch of them. You can do all these things. If that's true, if you have these 2 assumptions, strict exogeneity and the rank condition, meaning there's variation over this, this actually varies, then that OLS model will give you an unbiased estimate of the parameter of interest. Fixest, F-I-X-E-S-T, F-I-X-E-S-T. I'll post it in a second, Sebastian. Okay. I'm going to real quick show you this. Well, actually, let's take a 15-minute break. We're going to come back in 15 minutes, and then I'll review just a table, and then we'll move into the diff and diff material. So let's come back in 15. All right. Let me show you this here. All right. So my research agendas have sort of no, I've only had like a few true research agendas. I guess one of them was sex work. Another was methamphetamine precursor control policy, and then there was a couple of abortion papers. So now it's mental illness and causal inference. But like originally it was sex work. And so I did a survey of what I would just call internet mediated sex workers. It was always kind of hard to find the exact phrase. We had to I had to interview all these sex workers that were being reviewed on the internet. And I asked them, what's the phrase that they would prefer I use? And they pretty much said adult service providers was what there was a kind of like a phrase that was recommended. So I had a survey that I put in the field called Survey for Adult Service Providers, or SASP. It was a survey of internet-mediated sex workers. It was 685 respondents, 5% response rate from this scraping of this website that I had done. And I guess 5% means what? 13,000. Yeah, so I had like 13,000 unique providers. I don't remember why I'd even had gotten down to that low, but I had like cleaned it up and I had like decided I was going to just work with 16, whatever that number was, 13,000. Even then, the response rate is higher than 5%, but I cannot prove it. So I can only go with this conservative number, but there were a lot of emails that were dead that I only later realized that most of the emails, most of the survey was coming from currently active sex workers. And the further back in time I went using this scrape data, they were no longer active, but I had to include them in the denominator. That's partly why the work doesn't get as, I ultimately don't publish a lot with this survey, but I learned a lot. And there's two types of questions. When I did the survey, I went into it planning a panel. That was one of the things I did. Was I had a desire to do a panel method. And the way I was going to do it was I was going to ask them information about themselves, what I just would call static provider specific information, age, weight, schooling, all this stuff, and then dynamic information. But the way I was going to do the panel was I was going to ask essentially a time diary. And I was going to ask, but it was all going to be retrospective. So there's a lot of stuff, could break down, but that's how I was going to do it, or that's how I did it. So I asked them about their last 5 client sessions. And the idea was I was going to use fixed effects. So let's look at the only place I ever published this is in the mixtape. So I'll show you the panel now. So here's like the data that I'm going to, the model, and I'm going to be looking at hourly price. I'm going to look at log hourly price. I thought of it as a wage. So it was like the gross price that a client paid a sex worker divided by the length of time that was spent together times 60. So it was like an hourly adjusted wage. It's not so everything, that's the thing to keep in mind, and it's logged. And then I have a bunch of covariates that are unique to the provider, and then I have a bunch of covariates that are observable that are unique to the client or the session. And notice that this S means that it's a session. It's like the time period. Okay. And then I got a treatment variable. And the treatment variable, and then I've got an unobserved heterogeneity. This is like a unique person-specific random variable that I got an error term. So these are the two problematic things. These are causing the wage. And I want to know D. What's D? D is going to be unprotected sex with the client. Traditional question, those that you don't maybe care. That was like a traditional question in the economics of risky sexual behavior or for sex work was the compensating wage differential. Was unprotected sex getting a higher wage and a higher price? Did you have to pay higher prices? And the problem was you were always worried about selection. There could be like people that were providing that and they're different. And so I'm going to use the within variation. I'm going to use the fact that sometimes people are doing that and not doing that. And I'm going to try to isolate the compensating wage differential associated with unprotected sex that controls for that selection, controls for that unobserved heterogeneity. And for illustrative purposes, I'm going to do pooled OLS fixed effects and demeaned OLS, right? And so there's really like probably three things that I think people usually are pretty interested in: the unprotected sex part, the length of time, how much time are there like quantity discounts? Does the average price go down as you spend more time with the client. And what does that mean? What would that mean about the transaction? And then is the client a regular? There's other stuff too, but we're just going to look at this. Unprotected sex. Pooled ordinary least squares. Does not use any dummy variables for the provider. These are going to be provider fixed effects. Does not put it in there. 0.0138. That would be a 1% increase in wage. Nothing's there. Okay. Length of time. Now, this is a log on log regression. So this is an elasticity, a 10% increase in the amount of time, number of minutes, 10% increase in the amount of time spent with the sex worker. There is a 3% lower hourly wage. Okay. And it's a she takes a lower wage hourly. There's some sort of discounting that's going on, right? And then is he a regular? And if he's a regular, meaning what is a regular? Regular, I ask her, or I ask them. I have men, women, and non-binary people, but I ask. I say, is this client a regular? So it's up to her, but that always means the same thing. And what does it mean? It means, is it a regular? I mean, it kind of basically means she calls him a regular. And a regular just basically means I see this person regularly. I've seen this is not the first time I've seen them. And if it's a regular, they pay 4.7% less. And then I've got a client attractiveness on a scale of 1 to 10. And, for every 1 unit increase, it's a 2% higher. It's a 2% higher wage. Now, fixed effect. So there's a couple of things just to remember here. You need both of these, by the way. You need variation. Once you have demeaned the variables, there has to be variation in the data. The variation in the variable, the demeaned variable, just to identify the parameter. Okay. So just to identify the parameter. And if you demean it, and you've got like, say you have a woman who sees clients and she says every one of them are attractive. Then when you demean it, even though you've demeaned it here and you got rid of the unobservable, if there's very little variation in the data over time, the demeaning will actually delete it too, or leave it without much variation. So it can be a little bit challenging. It can be a little bit challenging sometimes to interpret moving from here to here. And you want to check to see how much variation there is in the variable. So unprotected sex, though, notice what happens. When I include fixed effects, dummies, it's a 5.1% increase, 5.1% increase in wages, right? Wasn't there before, now it's there. It's not quite significant at the 5%, level. The length of time, though. See, length of time ends up being very precise in a lot of this because they report a lot of these last 5 clients, they report a lot of different times. Okay. Unprotected sex, though, there isn't a lot of within provider variation. So, I do find things, but I don't have a ton of variation. And so, because the reason why I don't have a ton of variation is because there really is a lot of there's a lot of people will not do that in my data set. They will not do it, or they always do it. There's not a lot of switching over 5 clients. So I find a 5% increase. Standard error 0.028. The regular part gets more precise. 0.037. Standard error goes down a lot. And even though the coefficient is smaller, it's more precise now. If you are a regular, you pay less. You pay less. They pay less per hour than non-regulars, conditional on, being the same kind of provider. Then we do the demeaned OLS. Notice the coefficients are identical. 0.051, 0.051, negative 0.3435, negative 0.435, negative 0.37, negative 0.37. Look all the way down. 142, 142. Okay. What is different? Standard error. Why? Because when you do d-mean to OLS, the degrees of freedom corrections are not correct. When you run this regression here, and you did an earlier step of calculating the mean and then d-meaning, when you run that regression in your statistical software, the coefficients will be the same whether you use dummies or not, but the standard errors will not be the same. And the reason is because the standard errors are based on those degrees of freedom corrections, and they do not know that you calculated a mean. They don't know that this has been a transformed variable. So you never want to actually demean, but it's helpful to know that that's what it is doing. Okay. The other thing is too, with the demeaning, I have all these provider specific variables. Okay. The provider specific variables do not change over time in my survey. I can identify them with pooled OLS. Okay. Body mass index. I have their height and I have their weight. Body mass index can be identified with pooled OLS. Cannot be identified when you put in provider fixed effects because they are collinear with the provider fixed effects. Cannot be put in with the demeaning. Cannot be put in with the demeaning because they will be eliminated. Because when you take the mean of the body mass index for a provider and you demean, it deletes it. Including linear trends is very common. What a linear trend is people will, and this is something that we'll kind of talk a little bit more about. What is the linear panel trend? It's this. Let's say you have 5 time periods. Period 1, trend equal 1. Period 2, trend equal true. Okay, I'll go dot, period 5. Okay, including linear trends will usually mean, it depends, usually will mean the same thing to people as including, provider specific linear trends or panel unit linear trends. And what it means is this: you'll regress outcome onto X and interact the provider dummies that you're generating with the linear trend. Which means you have to now identify the panel fixed effects, the trend alone, and the interaction. So there's like a whole bunch of more. No, I'm not saying you recommend, I'm not recommending demeaning, Amy. I'm saying that when you run fixed effects, it is demeaning. That is mechanically what it is doing, including dummy variables for every single panel unit. It is numerically, algebraically demeaning the data and then running a regression on the demeaned. That is what it does. It's a transformation of the variables and does that. So when you do this here with this, now you're having to identify this linear trend. And so, if you don't have a lot of variation, you don't have a lot, if you don't have a lot of variation either in the left-hand side variable or the right-hand side variable, over time, okay, if it's like not a lot of variation, if it's like a variable that's like, if it's a dummy variable, there's not a lot of variation potentially that you might be working with. Okay. So you're going to, your linear trend here, this quote linear trend, you're going to need there to be enough variation around the trend just in order to do the actual OLS calculation. Okay. Because remember, what you need for OLS is that rank condition. There's got to be variation left in the data once you put in that linear trend. And sometimes, there's no variation left. So it's not really clear, like, am I over controlling? And so, so unprotected sex with any client of any kind. Okay. Well, I have a tremendous amount of sorting in the data into either being someone who does or doesn't do that. Once I put in the fixed effects, I'm exploiting some variation within the sex worker. When I put in the linear trend, interacted with that, I think I didn't really I haven't really dug into this too much, but I think that zero and that huge standard error is coming from the fact that I don't know how much of that is coming from the fact that there's just not a lot of variation. But this one, see, it's a highly variable. It varies a lot. Length of time varies a lot. Interestingly enough, regular varies a lot. It gets more precise when I put it in. So like the things I feel more confident about are, things that are changing over time. And, these kinds of things change over time. The race of the client changes over time. Where they meet the people changes over time, and the amount of time. But, the more you kind of put in provider specific trends and quadratics, it will, it can kill the result. It can kill the result for a lot of reasons. One reason being, you may not even have much variation left to even identify it because it's so collinear with that provider specific trend. And you're going to have to check that. You're going to need to check that and see how much variation there is in that variable once you sort of do all this additional stuff. And there may not be much left, which means, you've not really answered anything. So it's something for you to be thinking about. So that's not really a review of panel econometrics, though. No, probably not for the specification. There's not really for in many ways, the specification is the falsification, usually is how this is going, Camille. You basically traditionally, I was talking to the inclusion of the linear trend in the causal inference world is really just to try to support the robustness of those original results that you were finding here. You basically are like, here's my result. Let's just say it's about regular. Here's my result, negative 0.47. Put in fixed effects. Oh, it's more precise. Put in linear trends. Oh, it's even more precise and bigger. Okay. And then you sort of start to go, oh, okay, I think something's there. It's usually that's kind of the style of this. It's not really saying that's the correct specification per se. Although you could easily imagine somebody that loves the result at this point because they're like, oh, I put in all these trends and it still does it. Usually what's done is you'll have a table with multiple columns and they'll kind of slowly move through it. And the last column will be this one. The last column will be this one, but it'll be up to the author to kind of say which one is their preferred one. They'll have some reasons for it. Okay, so we sort of did not discuss random effects. We didn't discuss first differencing. We didn't discuss Arellano bond. It's not a panel lecture. Okay, it is a diff and diff workshop, and we're only really focused on two-way fixed effects. Okay, we're not even really focused on pooled OLS. I just wanted you to understand this demeaning. All right, so we're trying to really understand diff and diff. Okay, and to understand diff and diff, we're trying to figure out two-way fixed effects because most of the time, what people do is what they would do is they would they'd go into here, well, anyway, they'd go into, oh, there's still a John M. Olin working paper series. So they would go in and they'll run state level regressions. Usually it'll be a law, state level, laws, firm level, laws. It'll oftentimes be a law or a policy of some kind. And they'll put in, they'll do OLS models, treatment variable, dummies, covariates, maybe, maybe not, usually yes, lots of covariates. And then they'll put in panel unit fixed effects, time fixed effects. Okay. This is the thing we ordinarily have with diff and diff, was the 2 period, but we want to know about this one. We want to know about this one. We want to know about the performance of this estimator, right? In a diff and diff context. And which means, thinking about things like potential outcomes, thinking about things like what assumptions I'm going to have to assume. And I'm going to have a state level fixed effect here. And I'm going to have like a year fixed effect. I generalized it, repeated cross section or not. And what we want to know is like, can I interpret this here as an average treatment effect? Like when can I interpret that as an average treatment effect? Okay. And our hope was that, that coefficient, at least historically, people that wrote about diff and diffs that were like Josh Anger's students or whoever, they wouldn't really appeal. They would appeal to strict exogeneity. Like, I mean, I've got this interview coming out on Tuesday with Richard Blundell. And like, when I was like, go back through, Blundell definitely in the 90s, he does appeal to strict exogeneity. But there's like debates that happen, at least in my mind, because Hito Embens and Susan Athey say strict exogeneity is too strong. Why do they say that? Well, strict exogeneity imposes restrictions on the error term that requires certain things about the treatment effects. And we're going to talk about that, namely that the treatment effects don't change over time and that they're the same for all the people. So we want to kind of know, like, all right, can I ever interpret that as a reasonably weighted average over all the treatment effects? Is it ever interpretable as an average treatment on the treated? Okay. So we're going to look at, I'm not going to do this paper because I want to just get directly into this here. We're going to look at Andrew Goodman Bacon's. We're going to look at Andrew Goodman Bacon's paper real quick. Let me just think. We have 20 minutes. You know what? Actually, it might be better to use the 20 minutes to just motivate to look at a traditional two-way fixed effect style paper, so that at least you can kind of frame it in your mind as we go into this. This is like a trip. This is like a typical kind of two-way fixed effects diff and diff paper. It's by my colleague Mark Hoekstra and his co-author and former student Ching. Does strengthening self-defense law deter crime or escalate violence? Expand evidence from expansions to Castle Doctrine. I was joking to Mark. I bet I've presented this paper more than he has. And it's his paper. So 2000 and 2010, 20 states passed the Castle Doctrine law, or what Florida called Stand Your Ground. And what these were laws that allowed you in the United States to use self-defense, lethal self-defense, in public or in places that you were historically not allowed to. Right. So there were 5 waves. There's one in 05. It's just Florida. There's like about 13 in 06, and then it gets like, it's like 05, 06, 07, 08, 09. For the time period here, there are 5 waves of reforms, or 5 cohorts. Okay. And what these reforms did was 3 things. They made it so that a victim did not have to run away. Historically, victims had to to retreat. They had a duty to run away if they were threatened in public. They could not use lethal self-defense. They could fight back, they couldn't kill the person, right? If you killed the person in public, you could be charged with manslaughter or murder, even if it was in self-defense. It was not a commonly kind of known thing. It was, I mean, I guess it depended on the DA probably, whether he would charge and whether he would win or not. But it was you were supposed to retreat, and these laws allowed you to not retreat. You could use lethal self-defense in public or places that historically you weren't allowed to. And then there were these two big ones that really were big part of it too. One was if though let's say that you, for some reason, a DA, well, they basically did two things. They basically made it, the laws were done where you didn't have to retreat, and the DA and the prosecutor was going to have to always assume that in your act of killing this person, you were afraid. It was like reasonable. It was reasonable to be afraid. So that meant the DA was going to have to prove that it was that not a reasonable person would not have been afraid in that situation, and which Mark told me is impossible. That DAs told him, prosecutors and DAs told him that is almost an impossible bar to prove a negative kind of type thing. And then last one, these were criminal court, and this is civil court. And the civil court was, even if you were found not guilty here, you could still be found guilty in civil court and be sued. And the law actually also said you couldn't be sued. So this essentially made it inexpensive to kill people. It made them inexpensive to kill people because essentially the only thing stopping you from killing somebody would be your conscience, you know? But the other thing too, though, is if you're in a situation where someone's gonna attack you, okay, and they now know that you're like if I'm going up to someone, I don't want to trigger anybody, so I'm not going to use your name, but like if I just go up to John Doe and I say, you know, hey, give me all your money, and if you don't give me all your money, I'm gonna you know, kill you. But you can now kill me first. Okay, so like you can use lethal self-defense with me. Well, if I know that you're gonna kill me, if I do something, I might not ever attempt to do something in the first place. And that would be like deterrence. Okay, so you could deter people altogether by simply making it so that victims can fight back. But you also might cause victims to kill people that were not going to kill them otherwise. Okay, or that nobody was going to get killed otherwise. So they're going to I always mean to take this off. Sorry, ignore that part right there. These are the fixed effects. So they run this regression. Crimes, there's three kinds of crimes they're going to look at. They're going to look at falsification crimes. They're going to look at larceny, and they're going to look at car theft. That's going to be their falsifications, right? Because they're going to think, well, if you're passing these Castle Doctrine laws, if you're passing those laws because you are concerned about, if you're passing those laws because you are concerned, well, sorry, if you run this regression and let's say you find some effect of Castle Doctrine law on crime, it could be spurious. It could just be that states are passing these laws when there's crime waves. You know, it's like something about crime in general. So let's look at the effect of Castle Doctrine law reforms on things that they can't easily, it's not easy to justify how it would be affecting those things. Okay. So that's one thing. And then, so that's a falsification. Secondly, they're going to look at deterrence things. And the main deterrence things they're going to look at are aggravated assault, burglaries, and robberies. Those are the things in their mind they think, well, if it's going to deter anything, let's look at those things because those are kind of more violent crimes involving interpersonal stuff. So let's see if it does those things. And then last, they're going to look at the homicide things. Okay, they're going to look at the homicide because victims are not committing robberies. Victims are not committing any of those things. But victims, if they retaliated and killed someone, it'll be recorded originally as a manslaughter or murder. It might get cleared later as such, but it'll be recorded as that. Okay. So they're going to look at that. They're going to do this like typical, this is like a typical kind of model. They're going to do a bunch of different kinds of fixed effects. They're going to do region by year fixed effects. So they're going to load this thing up with fixed effects, which is going to affect the kind of assumptions. And then they're going to do different kinds of estimators. They're going to do two-way fixed effects. They're not doing Poisson. I keep meaning to fix this. They're going to do negative binomial. They can't. They can't, Sebastian. They're using the uniform crime reports, the stuff I was telling you about earlier. The uniform crime report, you can still publish well with the uniform crime report. I mean, my paper in Restud uses the uniform crime report too, but it's very limited because it just says counts. Doesn't tell you a lot about the people. They do have some data on a special data set on justifiable homicides, but for the most part, most of the results are on murders and non-negligible homicides. So they can't really do a whole lot. And they're going to do a lot of controls. But see, this is like this control stuff. It's not really the way that we've been motivating it. It's not really like, let's make sure that the states are, I mean, yeah, you could justify all this stuff, I guess, on the grounds of parallel trends, but they really justify their parallel trends here. They're going to do census region interacted with year. And what that's going to do is that's going to, let's see, Sudva, theoretically violent crimes. Well, Sudva Reese would be two things. Traditionally, Sudva means when Florida passes its law, it cannot cause neighboring states' homicides to change. So it's the no interference. Yeah, NIBRS is a very, I've written about NIBRS before they made it easier to work with, and it was I always felt like every time I went in to work with the NIBRS data, I felt like I was having to really get focused because it was such a pain merging all those different, across those different parts of it. I used it for a video game paper and I despised it. And perpetrators. Recorded murders by perpetrators. Yes. But SUTFA is about the panel units. It's about the panel units. And is there interference between the panel units? It's not about the mechanism. It's not about the mechanism. It says, when Florida passed its law, does it change homicides in South Carolina? And the states are the panel units, correct. So SUTFA is all about like, is there interference between when one state gets treated? Yeah, the unit is consistent, correct. Yeah, the unit is consistent. The panel unit is the aggregation of all homicides in that year for that panel unit. So you're just counting it up. And so you would just need it to be when a panel unit gets treated, is it causing another state to get treated? See, that can happen. With minimum wages, that can happen. Think about it like, where I live in Waco, if Waco was to pass a minimum wage, but Temple which is like 30 minutes away, Temple doesn't, that could easily impact the labor markets in Temple. It could cause people to travel between the cities. It could cause firms to locate in one city or another. It's as though they're getting treated, right? Sudva is all about this. Sudva is all about this. Y equals y dy1 plus 1 minus dy0. Your outcome is based on your treatment assignment and not someone else's, and not someone in the futures either. And treatment intensity is the same, correct? No hidden variation in the treatment. The dosage is the same. Sudva gets violated in these things all the time, and it's the big ugly secret that nobody talks about. But yes, exactly, Sabin. Well, I'm not saying that they're using it in a fairly standard, Eduardo, they're using it in a fairly standard way. They're thinking of it more like omitted variable bias kind of frameworks. And I don't really think of that as the same. And they're also using time varying covariates. So you've got to make assumptions about the time varying covariates, heterogeneity of the treatment effects with respect. So you're going to have to say treatment effects are the same regardless of the amount of police you have, regardless of the amount of imprisonment, race, etc. So it's a lot of strong assumptions. But I don't think, I don't think that Mark would probably have said that, in reading the paper. And Ching, I don't think that they would have said, they would have probably motivated it more by omitted variable bias than like about recovering parallel trends. They think of this as about forcing parallel trends. They're requiring that the neighboring states in the same census region to be the correct counterfactual. That's how not this part here is, but I mean, yes, finding states that have similar levels of policing, similar levels of imprisonment, similar race shares, makes sense, but that's not exactly what they say. So here's the deterrence effects. Deterrence should show up in a regression always, just so you can think about this. Deterrence always shows up with a negative coefficient, because it's basically saying, if you do more of this thing, you're going to get less crime. And look here, before I even explain what all these numbers mean, okay? Just for now, just notice nothing's negative. Okay, so this is burglary, robbery, aggravated assault. They also have a falsification category. Falsifications were not significant either. So that's like, they first started with their falsification, then they do it in a weird order. They start with their falsification, then they go to their deterrence, then they went to homicide last. It's kind of, I've always thought that was kind of interesting that they did falsification first to prepare you for their results. They rule out that there's anything else being, that their law is not associated with general crime trends. Then they say, all right, do we find any deterrence effects? Nothing's negative. What are each of these columns? This is a very traditional diff and diff column with two-way fixed effects. First, they're going to put in state and year fixed effects. Then they're going to put in region by year fixed effects. Region means census dummy interacted with a year. And that forces all the variation to be compared to other states in the same region. Then they put in time varying controls. That's this stuff. So that's column 3. Then column 3 and column 4 are the same. What's different? They don't do an event study. Not exactly. They have a bunch of unconditional event studies, but like, they don't do a regression-based event study. They just put in an indicator, whether it's the year before treatment. Okay. And that's it. And then they put in contemporaneous crime rates. What's that? So this last one is, once they've established that there doesn't appear to be any other effect on any other crimes, then they put on the right-hand side a bunch of crime variables. The other crime rates they put in. Well, a lot of people wouldn't do this now, but this wasn't even 10 years ago. So a lot of people would think that this is about, a lot of people would say this could arguably put in a endogenous variable on the right hand side, but they go to great lengths to say we can't find any effects of the treatment on those crimes, so we're going to put it in. So they put it in, and then the last thing they put in is state specific linear trends. 6 columns, different specifications, increasingly restrictive, a single coefficient, don't report any of this stuff. The table does not show any other coefficient except for this. It's like a fairly standard deal. And then the last thing is they have different estimators. OLS weighted, OLS not weighted, negative binomial weighted, negative binomial not weighted. So it's this huge kind of thing, nothing. Then they look at homicides, okay? So they do the negative binomial unweighted, they do the OLS weighted, they do the OLS unweighted, they do the negative binomial weighted, they do all this stuff. And they basically find very, very strong evidence that the Castle Doctrine law is increasing homicides and non-negligent manslaughter, non-negligent homicide. And it's of a range of around 5 to 10%. So here they have no region by year fixed effects, 5.6%, 9%. Put in the region by year fixed effects, jumps to 7, basically doesn't change. Put in the time varying controls, doesn't really, gets even more precise. Put in a event study coefficient, pulls it down a little bit. Now, I mean, part of this, these are fairly large standard errors, but it is not common to do it, Reese, because the way that it's calculated, is kind of the panel sample, sorry, the panel power calculations kind of vary a little bit, and they're more recently developed. So this is one thing, and it's a quasi experimental, observational kind of study, and you can do them, but you're not going to be able really to say a lot. You're not going to be able to really do anything about it here. So it is fairly uncommon to do power calculations in the non-RCT setup in econ. And for panel, I've only seen more recent methods that are developed for it, and there seems to be a little bit of some different ways to do it. So that's the other thing too. So no, you can't save it. You cannot do the interaction because you know what? I could show you. No, I won't have time. So they only put in state and year separately. They put in state and they put in year. You can't interact them. And the reason you can't interact them is because there is no longer that interaction is collinear with, there is no variation in their data set within a state year interaction. Yeah. State specific linear time trend. So that's why I was saying earlier, the state specific linear time trend, was literally this. They create a variable called trend, and it equals 1 in 2000, 2 in 2001, etc. Okay. Then they have state dummies, which they include. Then they interact state dummy with trend. So in Stata, it would be like, if you're used to using Stata syntax, it would be like this: XI, reg, homicide, treat, I dot, state, No, it would go like this. It'd be like state pound C dot trend. And you would have a coefficient for treat, coefficients on every state dummy, coefficient on trend alone, coefficient on every state trend interaction. It's like a whole bunch of other interaction. It's like it doubles, however many state dummies there are. Now you've got like a whole other doubling of it. So it's like another 50 parameters you have to estimate. And it's a state specific trend. And it usually kills things, but it didn't in this case. Notice how, like, compare it to all this deterrence stuff, nothing. But here it only really makes it stronger in negative binomial. And here it bumps up the standard errors and pulled it down, so it's not significant. But, for the most part, it's fairly robust. So that's like a fairly standard kind of two-way fixed effect stiff and diff. You had a series of robustness checks, all these falsifications. Like we said, that bite, you couldn't do bite. There is no bite, so they don't do that. They don't show, because it's not really clear what the bite would be. That'd be something to think about. What would bite be? Castle doctrinal forms change. It's not making you buy more guns, so you can't look at that. It's just, are there more? You would have to show, like, I don't even know what it would be. Like, are these happening in public or something like that? But they don't have that data. They might with NIBRs, actually, because NIBRs will tell you the location of a crime. That's kind of interesting. Robinson, you could do this with NIBRs and find the location of the crimes. Are they happening in public places? Homicides in public places? That's something you could do. But like Robinson said, NIBRs is notoriously missing lots of data, both by city and state and police jurisdiction. So it's just kind of like a big mess a little bit. You have to make a lot of strong assumptions about it. It's much better data. Anyway, so they do it, but here's what they end up doing. Mark's like, does all this stuff, Mark and Ching do it, and they say, okay, 8% net increase in homicides. Okay, these are homicides that never would have happened, both in aggregate and to people. So it's like, these aren't just changing who's getting murdered. So it's like, before in counterfactual, nobody was going to get murdered. These were interactions that would have not ended in a murder, but now it's like, not only is it ending in a murder, it's like, it's not just who's getting murdered, but it's like murders that nobody would have been murdered. Okay. All right. So we're going to take a break. We're going to come back in an hour, 1:05. We're going to dig into, our goal is to really get into Bacon decomposition, Callaway, Santana, Son, and Abraham. So that tomorrow we can also do imputation estimators and continuous treatment. But we're going to take an hour break now and come back for lunch, and we'll be doing some simulations and some coding together when we get back. Okay. All right. So I'll see you guys in just a minute. Bye-bye. Let me start while y'all are waiting to get back. I'm going to see if I've missed any comments. Especially the interaction, there is each of when you do the interaction, if your data is at the unit level, unit time, and you put in unit fixed effects, year fixed effects, you can still find correlations in the data because there'll be variation in the data. Within year, there's variation in the data because you've got, within a column of years, you've got lots of, units. And then with the inclusion of the unit fixed effects, you've got variation within the the unit. You can observe them over time. When you do both, unit, year, fixed effects interacted, the question you have to ask yourself is, all right, so you look at it like let me imagine a block of the data that contains Scott Cunningham in 2024. So say it's like Scott Cunningham observed over time, Anna observed over time, right? I have variation in Anna's outcomes over time. I have variation across years, within years over time. I have the different people. So I can block them that way, and I still have variables that take on different values. If I then was to set it and I was just to grab a single Scott Cunningham 2024. Okay. Question is, what's inside that Scott Cunningham 2024 block of data? And it's only one observation. It's whatever that is. Fixed effects always kind of like grab blocks of data, and then they do simple calculations, simple correlations within those blocks. Okay. And once you create a fixed effect that is at the smallest level of the observation, you cannot calculate any correlation within it because there's only one observation within it. So, the only way you could put in state year interaction is if your data was not measured at the state level. It would have to be many firms within a state, many people within a state. Then you could do it. So long as you have multiple observations in the data within your fixed effect, you can always do some kind of calculation. But when you literally fixed effect it out where that final fixed effect is just capturing a single number, it won't work. Yeah. No comment. I think tree equal one, tree. Oh, yeah. And that's the other thing too, is that's kind of a different issue, but the software packages, Todd brings a good point up. The software packages have to sort of be told ahead of time, this is a panel data set. And if it says this is a panel data set, they want to know, well, what's the panel identifier? And you say county. What's the time identifier? You say year. Once the software knows what that means, it kind of knows how to distinguish all of the dummies from one another. And then, it won't because it can't do all of the fixed effects. Like there'll always be some sort of multicollinearity. You put all of them in there, so stuff has to get dropped. So it has to be like sort of already structured in a way that recognizes the panel structure so that all of your ensuing commands make sense. How would you do it? It would be, well, we're gonna see that, I guess, Swati, with it's harder a little bit. It's a little bit more challenging to describe it for me. I haven't not prepped to answer that, but I would probably say there's a theorem called the Frischwald-Lovell theorem. And the Frischwald-Lovell theorem is the backbone of what this next paper is going to be that we're going to discuss. And the Frischwald-Lovell theorem, what it does is it shows the final result of taking out taking off the means. And so So what would it be if you had interactions? So like you could probably, so here it's always going to be a demeaning. So if you have county year fixed effects interacted and your panel unit is a county, then it won't even work. I mean, OLS requires, in order for OLS to do anything in the first place, there has to be, things cannot be a linear transformation of each other. The variables can't be. And so if you put in county year fixed effects, it'll violate, it's like dividing by a zero or something. It's just, it won't work. It won't work. So if you've got household level data within a county, you can put the county year fixed effects in. And so probably what would happen is, I don't know off the top of my head what exactly all the steps would be, but it'd be like county mean, year mean, county year mean. It's always going to be some version of a demeaning, but I don't know off the top of my head what exactly that would look like. Um, but it will always, I guess I'd have to think about that a little bit more. Somebody might know. Then, all right, well, so let me think about how the most condensed way to answer that might be. I mean, it's gonna be with the Frisch-Wald level, and I could sort of just sort of say like, take the average, demean it for one dimension. That's a new transformed variable. So you'd go like, take the average of the state of the county. It'll always be with respect to that unit. So it's like you'll have the household level data, but you'll do things with respect to the means over the entire county, means over the whole years, means over county in a given year. And you'll go through all the steps of demeaning. So you'll demean at the year level, demean at the state level, demean at the interaction level. And each time the variable is just getting demeaned, a subsequent demeaning. So it's like, we only looked at one demeaning, actually, when you looked back at what we were doing here. We only put in panel unit dummies. We didn't do two-way fixed effects. We did one-way fixed effects. We only put in dummies for panel unit. And that gave us a demeaned outcome, a demeaned right-hand side variable. We then put in year dummies. It would take all of these right here, okay, this like right here, and it would say, well, what's the average y dot dot for my data in a given year, okay? So that would be across the cross-sectional units. Takes an average, demean, so it kind of like, when you do that, it basically becomes like this. It's like, and what it becomes is like y, dot dot it minus y dot dot t, where y dot dot t is the average of y dot dot in a year. So you would have to you would do this like every single time. You would demean every year. Every variable gets transformed by its demean version over on this side and over on this side and over on this side. So, so then you have this like second demeaned, this like double fixed effects. You put in another one, you put in another fixed effect. It's like you just kind of, I mean, because you're going in order, I guess probably because of the additive property or something, because you're going in order, it doesn't really matter which order you go in. Now you're on this third one and you're like, all right, now I'm like, I'm a household in a given year, county year interaction. I'm a household, right? So I'm the Cunningham household 2024. County year interaction would be Waco, Texas, 2024. Take the average, but it would be this. Take the average y dot 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 dot, 4 dots, my transformed value. It's still just a transformed value in a given unit year. Take the average of every single Waco specific households in each year, but only for their demeaned. And then all of a sudden, I've got another thing. And, Rock said, it's slightly off topic, but one time I read a paper on surgeon performance. The authors had 5 million observation. Their fixed setup was doctor, day, hour. It's like, it's kind of wild. It's kind of wild. We're so used to fixed effects language that it's kind of like, well, let me just interact everything. And the way that people kind of, I think is they go, well, the more fixed effects I put in, the better. That's kind of like it's almost monotonic, people are like, well, the more I put in, the better. Until you start realizing it's like what it's doing, which is all this demeaning. And then you get really confused. You're like, what is this variable? Well, it's useful insofar as you're dealing with this problem. It's useful in so far as you're dealing with this problem, and it gets, but it's going to place a lot of restrictions. These fixed effects, as we're going to see, they will place a lot of restrictions on. They'll place a lot of restrictions on the regression model. Well, no, they'll place a lot of restrictions on the treatment variables. So my overall, I'm not saying there's anything wrong with doing it. My overall hesitation usually is, the less you can understand what this thing is that you're doing, the more cautious you should be. Doesn't mean everybody doesn't understand it, but it's like when you go through 6 different, levels of fixed effects qualitatively, because you're like, I'm just going to control for everything. And then you start to realize how many things you're demeaning. Well, first of all, just think about it. Think about it for a moment. There's a point where you can't do that anymore. There's like, I can only take the mean out of something so many times before there is literally no variation left in the data. Right? Because it's like I take a column of numbers, mean it, demean it, demean it, demean it. Like among all these dimensions, you demean it. You do it according to dimensions. All right. It all depends on how many dimensions you have. You do it to all dimensions, every combination of the dimension. At some point, some of the variables, though not all, but some of the variables that don't change a whole lot, that demeaning process might leave it so that it's just razor thin variation. And you're going to need a massive data set or to pick anything up, which might be why Rock said he saw somebody use a data set that had 5 million observations. Well, when you have 5 million observations, sure, you might be able to have a lot of variation left in the data. But the point here is that, you've got to be able to understand both, you got to be able to understand what it's costing you to do it too. Even before we even get into treatment effects, you may be shaving off all of the variation left in the data in order to pick up any of these correlations. These simple correlations cannot live. They can't. They might. It's not that there's not a causal effect. It just might be your data set might not have a lot of variation left in it. So now we're going to look with this panel data, and we're going to look with this two-way fixed effects. Okay. And we're going to talk about this Andrew Goodman-Bacon paper. So let me show you this paper. So, and I know I kind of like keep referencing Google citations, but it is absolutely mind-blowing how, completely life-changing these papers were for these people. Andrew Goodman-Bacon's paper shows up 2018. Yeah. They all come out around 2018. There's some 2016, 2017. They're all like either graduate students or assistant professors. All of this new diff and diff stuff is coming from young people. And I guess like that's how a lot of, revolutions in econometrics or science has been. It's oftentimes been very young people. Josh Angerist was a recent graduate of Princeton. When he goes to Harvard and work with Embeds, who had just graduated from Brown. So there's like that. So that's the Ivy late theorem. Heckman does his pioneering work in the 70s when he's not been out of school a whole long. Orley Ashenfelter does all that time at industrial relations section when he hadn't been there very long at Princeton. He had just graduated. So there is this like transformative work that typically is done by young people. And this is no different. It's like all of this, but it's actually kind of interesting too when it is done by young people. Their social networks have not yet formed. This is my interpretation of it. Their social networks are still, their professional networks are new. Okay. So Carrill is at Harvard. Andrews at Vanderbilt. Pedro Santana is at Vanderbilt. Brant Calloway had been at Vanderbilt. Bean Zhao had been at Vanderbilt. There were 4 Vanderbilt people. They only start to really meet the other people as these papers take off, which I think surprised everybody. I mean, Andrew, when you look at Andrew's vita, it's an incredible vita. Andrew's an amazing public finance, labor, economic historian. He's mostly known now for a lot of this diff and diff stuff, but because his top 2 most cited papers are diff and diff. One's the continuous treatment, and one is the this paper. This paper exploded. Shows up 2018, 360 sites. A year before it's even published, it's got 360 sites. The year it's published, 775. Year after, 1424. Last year, 1938. This year, 479. It might be slowing down. 479. Wonder what page is that? Pedro's going to overtake him. A lot of the estimators are overtaking Andrew because, for reasons I'm going to explain, Andrew's paper shows the problem with this model. It does not develop a solution. See, and that's what people want. Nobody wants just to be told there's a problem with your model. People want to be told there's a problem with your model and I have a solution. Okay. And Andrews was a diagnostic, or it was a diagnosis. It was like a doctor that says, I have bad news, as opposed to a doctor that says, I have good news. And Pedro's paper is, I have good news. And Andrew's paper is, I have bad news. And then the DeChase Martin and DeHolfel, as well as Sophie Sun and Sarah Abraham, as well as Karel Borsak et al., those papers were both. They said, I have bad news. 2A fixed effects is flawed or biased. And I have good news. I have a solution. Take this pill and it won't be biased. Or no, sorry. Take this, use this tool. And this tool will work. Okay. And it's just been like it's been a lot of work to get people to understand these issues. A lot of mixtape sessions has been about trying to do that, and so to help people so that this can be a lot more smooth of a transition. So anyway, what Andrew does is, in the paper, he uses that theorem that I mentioned, the Frischwald-Lovell theorem. The Frischwald-Lovell theorem is just a way of showing the demeaning. And it's a way of basically taking a number like we did here, okay? Like what we did here. And we said, all right, well, you can either do fixed effects or you can demean. They're the same thing, okay? And so what he does with the Frischwald-Lovell theorem is he says, all right, run this regression. I'm going to get a number. I'm going to then decompose that number into causal effects and bias terms and show you what you must assume in order for this to be unbiased. Okay. Now, what he's going to do, first of all, is he is going to show that in the diff and diff, the 2A fixed effects, this particular number that you're going to get, that coefficient, ironically, just like this was equal to 4 averages and 3 subtractions, this is also going to be equal to 4 averages and 3 subtractions. Specifically, it's going to be equal to a weighted average over all possible 4 average and 3 subtractions that are in the data. That's what he's going to show. He's going to show that that coefficient, when you estimate it with OLS, when you estimate this model, and you've got a binary treatment, this coefficient is equal to a weighted average of all possible diff and diff calculations in the data, where diff and diffs are 4 averages and 3 subtractions. But there's a bunch of them. And you can think to yourself, well, what does that mean? How could there be a bunch of diff and diffs when I thought that this was diff and diff? See, for a long time, for a very long time, people thought diff and diff was fixed effects. They thought it was the same thing. They thought diff and diff was the identical to fixed effects. And it's not. Fixed effects is an estimator, diff and diff is a design. Okay, and you can get a diff and diff using outcome regression. You can get it doing this 4 averages and 3 subtractions. You can use it using Heckman, Ickemer, and Todd. You can use Abity. You have all these options for doing difference in differences. Okay, and he shows that linear regression model will yield a coefficient that is a weighted average over all possible difference in differences calculations in your data set. Okay. So even before we even get into causality and think about parallel trends and treatment effects, the first thing Andrew showed was just how is this numerically calculating that number? Just like we did just a minute ago by showing like the demeaning, he did that here. But the weird thing was he showed was, and now it seems obvious, but like I think a lot of people did not know this, is that two-way fixed effects, ordinary least squares, when it is calculating that, when ordinary least squares is doing those calculations to create those weights, to create when OLS is calculating that number and getting there by calculating diff and diffs and then adding them together with weights, it calculates both the 4 averages and 3 subtractions, and it calculates the weights. It makes up its own weights. And those weights are odd. And they're not necessarily the ones that you or I would have picked. If I had told you, hey, here's 10 different diff and diffs, take a weighted average of them, you would probably weight them all the same. You would say, all right, add them together, divide by 10. You would take like a simple average. OLS doesn't do that. So that's the first thing. So before we even get into how to interpret the causal part, let's look at what two-way fixed effects is doing. So to understand that, we first have to kind of understand this idea of how can a data set contain multiple diff and diffs? How is that even possible, right? So we're going to use the letter K. And what K is going to do is it's going to refer to timing groups, all right? Timing groups. So we're going to have 3 timing groups. Ordinarily, what we had before was 1 timing group. Okay, so like with Card and Kruger, minimum wage, paper, New Jersey was the only timing group. It was treated with a minimum wage increase in April 1992. That's what it was. April 92. Okay. 1 group, 1 treatment group, 1 comparison group. Pennsylvania. Versus, imagine there were 3 treatment groups. New Jersey gets a minimum wage increase in 1992. Call that Group A. New York gets a minimum wage increase in 1994, Group B, and Washington, D.C. gets a minimum wage increase in 1996, Group C. And then we have Texas. Texas never over this period raises its minimum wage, making it Group U. Okay. So if we approach it in the way that I'm saying, you can calculate 9 different diff and diffs. Okay, 9 different diff and diffs. Now I'm just gonna do one, for example. We could go like this. We could go 1993 employment minus 1991 employment for Group A compared to Group B. And we could go 1993 employment minus 1991 employment for Group A compared to Group C. So that'd be like Washington, D.C. This would be like New York. This would be like New Jersey. And then you could go 1993 employment minus 1991 employment for Group A, New Jersey, compared to Group U, Texas. Okay. So we could do that. That's 3. That's 3 diff and diffs. Okay. It's 3 diff and diffs. Could always do this though. We have another one. We could go 1995. This would be for Group B. And Group B is going to be New York. Now, Group New York is our treatment group. And now we're going to compare them to Group A. All right. And so now it's going to be 95 employment minus 93 employment for Group B compared to who? New Jersey. Notice here, notice already treated is the comparison group. New Jersey was treated over here. Now all of a sudden it's getting used as a control group. Okay, we did this actually on last Sunday. Remember we had that example, we had that homework where we went through and we said, you know, what will the assumptions be if you use an already treated group as a comparison group? And we said parallel trends was not enough. This is where this is going to start to come in. So you have here New Jersey compared to 3 groups with respect to its timing period. New York compared to 3 groups with respect to its timing period, and Washington, D.C. compared to 3 groups with respect to its timing period. U is never treated, so it's never on the left-hand side. It's always can only function as a control because it doesn't have a treatment date. So when you have, you know, K timing groups, ABC, 3 of them, and you have 1 untreated group, you have K squared diff and diffs in your data set. Okay. And what we're going to show, or what I'm going to say, is that ordinary least squares, the problem with ordinary least squares, or the problem with this specification, is that ordinary least squares, is going to calculate every diff and diff and take a weighted average over every diff and diff, even ones that use already treated groups as controls. It's just what it does. This, when you tell OLS to run that regression, right there, that one, you're telling it to calculate every single diff and diff, and then calculate every diff and diff, take a weighted average over all 9 of these. And I don't mean the weights are 1/9. It might weight this one way more than that one. okay, for reasons that are contained in the properties of OLS. Okay, so let's look at a really simple example of two groups, group K and group L, and we're going to have a third group U that's never treated. Okay, so we have these notation here. We have group K and group L, and then we have one untreated group. K and L differ with respect to when they are treated. D bar is going to be the share of time that a group is treated while it's doing that. All right. So let me illustrate this with okay. So we said D bar share time each group spends treated. What does D bar mean? The mean of D equal average. That's all it is. Okay, so where you see this letter here, D bar, for group K or whoever, it just means what percent of the time were they treated? So if it, they weren't spending as much time treated, then it changes D bar. Okay. All right, so let's have three groups, group K, group L, and group U. Okay, group K, it's going to be observed over time. Group L, it's going to be observed over time. Group U, observed over time. Right? And then this is the measuring the outcome. No, none of these are potential outcomes. These are just realized outcomes. All right. This is going to be the pre-period. This is going to be the post-period. This is going to be mid. Pre-K, post-L, mid-KL. Well, we have two groups, one untreated group. So that means we have two squared diff and diffs, 4 diff and diffs. Okay. We have here early to untreated. Okay. So we're going to go, what I'm going to do here is I'm going to actually do the calculations so that you can see it. Let me change the color. Right. So look at this. Average, 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 average. 4 averages, 3 subtractions. Average for group K in the post. Like about a 34 minus. It's 34. That's a 20. Post K, group U. Let's say that's an 11. That's an 8. So I'd say it's like a 14 minus a 3. That's an 11. Not causal, because until we invoke potential outcomes, nothing is causal. Nothing is causal. It's just a number. That's all it is. It's just a number of the change in one group versus the change in another. That's all it is. Till we invoke parallel trends and all that stuff, it doesn't mean anything more than that. Then we have group U, group L, and group K and group L. These two diff and diffs are interesting because they're both being compared to an untreated group. They're both being compared to an untreated group. So here the untreated group is group U. Here it's group U. This is comparing group K to a not yet treated group. So this is like one of the things that OLS does is it goes like use the full data for group K, use the full data for group L, use some of the data for K to L, use some of the data for L to K. Okay, so it's going to go calculate the average of K here, average K here, average of L here, average of L here. Take the four differences. L is not treated. So look at these. U is not treated. U is not treated. L is not treated. Now look at this one. This is group K in the group L in the post. So that would be that number minus that number minus that number minus that number. But the difference is, whereas here the comparison group is always untreated, always untreated, always untreated, completely treated the entire time. So I now have as a comparison group, I'm using as a comparison group a already treated unit as a control. And we did this in our homework last week. We know that that creates issues. Okay. So what Andrew's going to do is he's going to take that regression, importantly enough, with 1 and 2 fixed effects, two types of fixed effects, and he's going to decompose that using the Frisch-Wald level theorem. And what he basically shows is that that number right here is equal to a weighted average of all the diff and diffs. We said there were 4. Okay, so here there's 2 groups, one untreated. So that's one, that's one, that's one, that one. So it does all 4 of them. It does all 4 of them. And then, having done all 4 of them, it then weights them. Oops. And it weights them by positive weights. Positive weights. SKU and SKL are the weights. Okay? So look at this. Look at this for a moment. This weight right here and this weight have to sum to 1. Right? So there's some properties of those weights. Number 1, SKU plus SLU plus SKL equals 1.0. Okay? They must sum to 1. Each weight is non-negative. Actually, is positive. It's not just, it can't even be 0. It's positive. There are no negative weights. You've heard of negative weights. That in Bacon's decomposition, there are no weights. Okay? In Bacon's decomposition, there are no weights. Sorry. In Bacon's decomposition, there are no negative weights. Only positive. So what's happening here is that coefficient is a weighted average of that diff and diff. Let me put it different. It's a weighted average of that diff and diff, that diff and diff, that diff and diff, and that diff and diff. Positively weighted. Now, how these weights are determined is based on group and time shares. SKU is equal to the product of, number 1, the average share of panel units in the treatment group, 2 times average share of panel units in the comparison group, times D bar, share of time treated, times 1 minus D bar, share of time not treated. Okay. Points 3 and 4 are called variance in treatment, whereas the first 2 are just some kind of group share. Okay. So I'm only going to focus on this one because this is basically the same thing, but you just have to slightly different interpretation. So I'm just going to do this. So this right here, the number of units treated cannot be negative. So that's positive. That's positive. And, D bar cannot ever be, there's nothing that could make D bar, there's nothing that could make D bar negative unless it was actually negative. Okay, then it could do it. Okay, so I'm gonna take a quick 15-minute break, and then we're gonna come right back. Okay, we're gonna take a 15-minute break. We'll come right back. All right. I will, for questions like that, I'll need to give it more time. Wait, no, actually that I can't answer. So raise it. Survey data, two time period, 9905. 9905, their treatment happened staggered. Yeah. There's probably a lot of ways. I mean, we're gonna be able to look at a few different ways. Um, but is it the treatment is getting more intense, or is it multiple treatment dates? Are these you have a treatment that happens in 1, 2, 3, 4, 5 years? Say staggered. Does that mean different groups or the same group? Ah, different groups. 99. Ah, yeah. Well, that's what we're going to look at. You have a lot of ways we get to do it. We have several ways that we're going to get to do it. Um, and when we see what our options are, the choices between them are fairly pedestrian. They're not like the biggest deal, but I'll show you. Okay. So you've got here these two elements that are you could do that you can do the Callaway. Yeah, we'll get into one of them today. So here's this weight on that particular 2x2. Here's a weight on that 2x2 as well as that 2x2. And this 2x2 is the treated group compared to the never treated. And this is the treated group compared to the not yet treated. And this is the treated group compared to the previously treated. That exhaustively describes all possible diff and diffs. First, we're going to look at these weights. Then we're going to look at these diff and diffs. All right, so there's the weight. The weight has basically two parts. The denominator doesn't matter because the denominator is a variance in the residualized treatment. Doesn't matter. It's just a constant. Everything's getting, kind of like scaled by that positive constant. So it's not really changing the it's not gonna change the sign for now. So put that aside. Let's look at the numerator. Okay. This is the percent of the panel units that are in group K. So that would be like this. Okay. So let's say there was like 50 states, 10 in group 10. K is 10 states treated in 2011. L is 10 states treated in 2015, 2013. And then U is going to be 30 states never treated. All right. So if we have here SKU, okay, SKU, then that's going to be equal to NKNU D bar 1 minus D bar. Okay. And so we'll go like this. We'll go NK, that's going to be 10 states out of 50 times NU 30 states out of 50 times D bar, which is 0.83 times 1 minus 0.83. So we'll go 10 over 50 times 30 over 50 times this times 1 minus this, and that becomes the weight, 0.016. All right. But let's say that we had this would be like, DK. Say we had DL, right? DL would be like it's going to get treated in 2013. Okay, so we'll go equal average. This, it's treated a little bit differently. We'll go SLU equal to our SLU. It's going to be the same thing. 10 over 50, only 10 of them. 30 untreated. Okay, so that's the same. Times 0.5 times 1 minus 0.5. So we'll go equal 10 over 50 times 30 over 50 times this times 1 minus that. Oh, it's bigger. It's bigger. Okay. So even though this was kind of interesting, even though it's the same weighted group, okay, even though it's the same weighted group of units, it will and the last part of it is this, like the reason this is what ends up causing it to sum to 1, so we're just ignoring that part. But the numerator here is they're all getting the exact same denominator, so it for our purposes we can just look at the numerator. Even though group K and group L have the same number of states in it, the fact that this one was treated 2 years later is causing the weight on it to go up, right? So we want to kind of understand that a little bit better. So let's look at 4 different scenarios. Let's say that D bar was 0.1. How would that work? So that would work like that. Treated at the end. Okay. Treated at the end. So when it's treated at the end, it spent, on a 10-year, it spent 1 year treated, spent 9 years untreated. 0.1 times 0.9, because see, it's 0.1 times 0.9. That's 0.09. Okay. Let's say we went a little bit earlier. 0.33. Notice how when we watch what happens here. Watch this right here. Okay. Give it more time treated, the weight goes up. Give it more time treated, weight goes up. Watch this. Weight goes down. Okay. So what you see here is that the weights on these OLS weights, it's not like they're going, it's not like this, like, you spend, less time treated. See, it goes up. Spend less time treated, goes up. You spend less time treated, goes down, goes down. So it's doing this thing here. Yes, it's favoring maximum variance with the unit. I'm missing my. It's specifically doing this. Okay, so it's like this is not time. This is going to be D bar. Okay, it's going to be share of time treated, right? And then this is going to be D bar 1 minus D bar. And this is the variance in treatment. Okay. If you look closely, okay, let me do this here. d bar 1 minus d bar equal this times 1 minus this equal this times 1 minus that. Okay. Look at that. The variance of treatment is the same for both of these. This one spent 83% of the time treated, but its variance of treatment was 0.138. This one spent almost no time treated, but its variance of treatment is 0.138. Okay. So we go up, watch. Variance goes up, variance goes up, variance goes down, variance goes down. So what's going on here is that it's forming a parabola. And the max is 0.25. The largest the variance can be is 0.25. And where does that happen? Watch where it happens. Okay, watch this part right here. When does it hit 0.25? There. 0.5. You go down again, and the variance of treatment goes down. So what we've been doing here, what we were basically doing was we were climbing this, okay? We were climbing it. The variance of treatment was going up. The more that it was treated till it hit 0.25, which was at the middle of the sample, and then it goes down, which means that it prefers or OLS favors, basically means the OLS weights are favoring or weighting up those panel unit diff and diffs. Okay, it's not the panel units, it's the panel unit diff and diffs whose panel units were treated closer to the middle of the panel. OLS has this like, centrality. It has this kind of like centrality favoring. And so it's if like group L was treated in 2013, but group K was treated here, right? So it's like group K is maybe group K has this D bar and group L has that D bar. Well, your final diff and diff coefficient is going to weight up some of those diff and diffs and weight down other diff and diffs. For not really for all that policy relevant reasons too. It's not like it's saying that it's not saying that that group L is a more reliable diff and diff. It's just saying in order for it to solve that constrained optimization problem or that optimization problem where you solve for the sum of the squared residuals, you find a set of coefficients that minimize the sum of the squared residuals. The way that it does that, the way that OLS minimizes the sum of the squared residuals is to choose weights that favor the stuff in the middle. That's what it does. It's not really like a causal. It's not done for causality reasons. It's done for fitting the best line reasons. Okay, it's done for the fitting of the best lines because you told it to minimize the sum of the squared residuals. Oddly enough, in order for it to find a line that minimizes the sum of the squared residuals, oddly enough, it chooses a set of weights on all these different diffs where the weights are largest for those treatment groups that are treated in the middle. It's very, very odd. And it's not something probably if I was to tell you, if I was to say to Sabin and say, Sabin, here's 4 different treatment effects for 4 different groups of people. Tell me what the weighted average of those 4 are. 9 times out of 10, Saban's probably going to go, well, without any other additional instructions, if I had to just decide what I thought the best, what I believe Cunningham was wanting, I'll just add them together and divide by 4. But see, OLS doesn't add them together and divide by 4. OLS adds them together. Well, it doesn't divide by anything. OLS says, here's this number times this weight. Add it to this number times this weight. And as you get closer to the ones that are treated in the middle, the weights go up. And as you get further away from the ones in the middle, the weights go down. And so that final two-way fixed effects coefficient is just going to be a weighted average over oh, did I say sample size? Yeah. Yeah. I think that's a good point. Yeah, I agree. Thank you. Yeah, that doesn't, because that says size, not share. Yep. So the weights on the treatment variance is maximized. So we say, like, is it favoring the maximum variance within a unit? Yes. And where is that, Reese? That is in the middle of the panel. That's in the middle of the panel. Okay. Let's skip that one. So groups in the middle of the panel, get weighted up, groups further away get weighted down, and not because theirs are more reliable and not because there's something better. And so this is the odd thing, but there's 60 of us on the call, If I gave you, if we all had an assignment and the assignment was, go study this question and go create your own panel, but I give you the data. We're not going to have to do much cleaning. I give you the data, but all 60 of us kind of make different decisions about, am I going to start the panel at 2010 and go to 2015? Am I going to start it at 05 and go to 2015? Am I going to go 2000 to 2015? Am I going to go 2000 to 2020? See, like, all of these decisions, they seem like they're small. They seem like ridiculous. Like, why would they even matter? Because you presumably would be hoping that you're estimating an average treatment effect for each of the units, and you could just weight them. But the thing is, all of us might come up with different panel lengths. And weirdly enough, simply by adding years to the data, we end up changing the weighting scheme without even meaning to. And Stata and R and Python do not spit these out. So you'll never know that you're doing it. So different choices about the panel length, what they're going to do is they're going to have 2 effects on your estimate. One is, because each of these are just simple differences in means, when you change your panel length, you're going to either change the number of years post, or you're going to change the number of year pre, or both. And when you do that, you're going to change your diff and diff. But you're also going to weight them differently. Some stuff that maybe was in the middle of the panel starts moving away from the middle of the panel. Some stuff that was not in the middle of the panel suddenly moves into the middle of the panel. It depends on how radically different these lengths are. But it's probably not going to be a huge thing. But it's just, again, us realizing that many of us didn't even know it was doing it, right? That's more of the issue, is that the estimator is doing things that many of us didn't know it was doing, and we had not asked it to do, and yet it's doing it. All right. So, but now what we want to know is, okay, so now what we want to know is, all right, I know that it's numerically going through those set of calculations. It's calculating those weights based on group shares and variance of treatment. And then it's calculating different diffs and it's weighting them. Right? It's getting that number. It either gets this number using that X dot dot prime, X dot dot X dot dot prime, X dot dot inverse, X dot dot prime, Y dot dot prime, it's whatever. It's like, it's either going to use the matrix expression, the matrix X prime X inverse X prime Y, well, in the transform data, or you could also, this is what the thing we're saying, you could also literally go through, find all K squared diff and diffs. You yourself could do this. Go through and find all K squared diff and diffs. So that literally, you could literally calculate this. Okay, this is a weird thing. You literally calculate that number by just simply calculating all the weights off of, this expression, calculate all the weights, all of which are means, okay? And then do diff and diffs for all K squared diff and diffs, and then add them together and multiply. If you did that, you would get the identical number than what you would get using fixed effects in a regression. Be identical, numerically identical number. Okay. So, but that still does not tell you if it is unbiased. Okay. So what we've got to figure out is if it's unbiased. So what we've got to do to figure out if it's unbiased, what we've got to do is we've got to take these expressions here. We've got to take these expressions and replace them here with potential outcomes, which, if you remember, I did that, right? Like I did that earlier last week. I took this and I was like, here is the means. So it would be like that mean right there. Here's this mean. I'm going to replace them with like their potential outcomes. So it's like, Y1 minus Y0, Y0 minus Y0. So this would be treatment group post mean of Y. That'll be a Y1. So that's going to be Y1, Y0, Y0, Y0. That'll collapse into a simple parallel trends. Y1, Y0, Y0, Y0. That'll collapse into the simple parallel trends. Y1, Y0. Look, Y0, Y0. That'll also collapse into a parallel trends. And then this one, Y1, Y0, Y1, Y1. And we did that one together. When we did that one together, what we realized was that this diff and diff does not collapse into a standard expression. It's not just average treatment on the treated plus parallel trends. It's average treatment on the treated plus parallel trends minus the change in the average treatment on the treated in this period minus this period for that group. We did that last Sunday. So we're going to replace it. We know that that coefficient is weighted average of all those. So all we're going to do is we're going to replace that diff and diff with its potential outcomes expression and do it for all of them, including that one. We're going to see, what does this coefficient equal? There's the KU, and there's an LU that goes with it. KU and LU, average true on the treated, parallel trends, K to L, average true on the treated, parallel trends, and then this one. The late group compared to the early group is the ATT for the late group in the post period, plus this parallel trends bias term, okay, minus the change in ATT over time. I encourage you to go back and look at the Sunday recordings. We did it at the very beginning of class. We did it at the very beginning of class on a sheet of paper. And you can see how we get to this. We did it on the very first day of class. There's all that stuff about the Bacon decomposition and the bias of two-way fixed effects. We did it on the first day. And when we did it on the first day, it was not about two-way fixed effects. It was simply about using an already treated group as a control. That is what the problem with that two-way fixed effect specification is. It's not OLS. It's using an already treated group as a control. That's the bias. The bias is not OLS. The bias is using an already treated group as a control, and the fact that OLS lets itself do that. That's the problem. And why does it let itself do that? Why does it let itself do that? Weirdly enough, that regression tells it to do that. That regression right there says take every diff and diff and then take a weighted average, even the bad ones, even the ones that we know from our, 45-minute thing we did last Sunday. We know not to do it. OLS doesn't know not to do it. Well, no, it's not even that. It's not that OLS doesn't know not to do it. It's that you told OLS to do it. You told it to do it. It's not OLS's fault. That equation says to do that. It's kind of weird, but like that is something that I think a lot of people had no idea of. Okay. And again, it's just part of the mystery of ordinary least squares that ordinary least squares has so many like duality kinds of interpretations to it. You can look at the same coefficient in different ways. That's what these decompositions do. Okay, they kind of show you that there's like different ways of looking at the same thing, and you can see, on this side it's doing this, but on this side it's doing this other thing. And when you look at it in both ways, you realize it might not be doing what you wanted it to do. But, it's not like our software just spits that out. So Bacon is going to plug in each of these into that expression here. Okay, he's going to plug it in to each of those expressions like this. This is going to go there. This is going to go there. That is going to go there. Now, when it does that, there's a few things to look. That weight will weight all of those. And that weight, since it's doing it for that one, will also weight all of those. Okay? So it's going to do that for all of them. All of them have an ATT. There's an ATT in that one. And all of them have a parallel trends. There's a parallel trends in that one. But only that one has this. And it's a minus sign. Okay? It's a minus sign. So you can group them, which is what Bacon does. He groups them. He puts them together, and he says, this two-way fixed effects coefficient, it's equal to the weighted average of the ATTs for each group. Group K in the post, Group K in the mid. See, Group K in the post, Group K in the mid. Plus the ATT of the L in the post. Plus the variance weighted parallel trend. So look at this. Now we have essentially, now you're realizing it. Well, I have more than one parallel trend assumption. I have 4. I've got a LU one that I've kind of buried and hidden it in here. I've got the Kate that says L. I got to fix that too. Fix the L subscript on my two-way fixed effect slide. So you've got a K to U parallel trend. We got an L to U parallel trend. We got an L to K parallel trend. There, that should be a K. And then we got a K, that should be K to L. That should be L to K. They're all in there. Minus, you can't see it, but it's down here. Minus the dynamics. The dynamics. If group K's here, if group K's treatment effect in this period, it's actually not this line, in this period, if this group K's treatment effect in this period is smaller than the treatment effect in that period, then it'll be like this. Let's say in the post period, let's say it's in that second period, let's say the ATT was a 20. Let's say in the first period, it was a 10. That's a 10. But look, it's minus a 10. It subtracts it. It subtracts it. It attenuates it. It attenuates it. Pulls down coefficient away from the truth. And there's a negative weight on it. Here's where the negative weights come in. You hear all this time about these negative weights. The negative weights are not here. These are not the negative weights. The OLS weights are not negative. It's the weights on the treatment effects that are negative. It's the weights on the treatment effects that are negative. So I'm going to do a simulation. All right. We're going to do a simulation. We're going to do it in Stata. I have it in R, but I find that the Stata is better for the teaching part because the Stata, yes, Charlie, the typos are right here. That should be a K. And that should be a K. Right there. And Sabian was thinking also this should say group share, but I'll fix that too. So it's just K to U, and then it's K to L, because it should basically always go in the order of this one should match that one. So it's like that one matches that one. That's the K. That's right, K. But then this should be K, K. It should be K. Okay, I'll fix it in just a minute. All right, so let's look at a simulation. All right, let's look at a simulation. I'm going to have 1,000 firms. I'm going to have 40 states. I'm going to have 25 firms per state. And I'm going to have a panel that goes from 1980 to 2009. It's going to go for 30 years. It's going to give me 30,000 observations. Some people really just feel more, their brain turns on when they see these things in Stata or R. So the simulation can really help a lot of people. And I want to go and help. I want to be talking to both people at the same time. So we're going to have here baker.do. You have baker.r also. Okay. So we said we're going to have 1,000 firms, 40 states, 25 firms per state over 30 years. So I'm going to go 1,000 firms, 40 states, 4 groups, 30 years. Quit. My cat. So we're going to go set observations to 40. That's going to be our states. Expanded by 25. Now I've got 25 firms per state. Then I'm going to expand it again 30, and that's going to give me 30 years per firm. Count. Display. We're going to go 40 times 25 times 30, 30,000. All right, so I have 30,000 observations. And then what I'm going to do is I'm going to create 4 groups. And the group is going to be a treatment timing group. All right, so I'm going to have 4 groups. The first 10 states are going to be in group 1, the second 10 in group 2, the third 10 in group 3, the last 10 in group 4. Okay, that's my groups. And then I'm going to give them treatment dates. Group 1 is going to get treated in 86, group 2 in 92, group 3 in 98, group 4 in 2004. And then I'm going to create a dummy variable equaling 0, 1, whether if in that period you are treated yet. So here's my firm. This is a firm fixed effect. Doesn't really matter, but it's going to be an intercept that we're going to use to generate data. And then this is going to be a firm identifier. So I'm going to have here 1,000 firms. Okay, 1,000, sorry. Yes, 1,000 firms observed over 30 years. Okay, and I got 25 of them in each state, and I have 40 states. So 25 over 40, that's 1,000. 1,000 for 30 years, that's 30,000. And that's our panel dimension. That's our panel size data set. So firm 1, okay, the letter N is a counter telling me, if time has passed. So it's 10 years since the start of the sample. 1980, 1989. Okay. All right. So firm 1 is part of group 1. Group 1 is states that were treated in treatment in 1986. But right now, row 1 is 1980. So it's firm 1 in 1980. Firm 1 is not treated until 1986. Therefore, firm 1 is not yet treated. 1985, firm 1 is treated in 86, not yet treated. 1986, firm one, treated 1986, it is treated. Okay. Now what I'm going to do is I'm going to generate some data. So I'm going to do, I'm going to give, let me show you what I'm going to do. All right. So what I'm going to do is I'm going to generate this and this, and you'll be like, what is that? So, okay. So here we've got, a spreadsheet, okay, where each cell is going to be an average treatment effect for that group in that year, right? So I'm going to have two kinds of average treatment effects. Let me just show you in the here. Here's the data generating process. So I'm going to have an error term that's on average 0 with a really small variance. Okay. And then I'm going to have a treatment effect called treatment effect 1, 2, 3, 4. And treatment effect 1 is going to go to group 1. Treatment effect 2 is going to go to group 2, and so on. And it's a little noisy, but the number is basically, TE1 is basically, you can see it here. It's on average a 10, but it goes down to like a 9.85 to a 10.15, but it's on average a 10. Goes from 984 to 1016. It just created a little noise. Not a big deal, but I just did it anyway. And then and so we did that. So now we have 10864. And now I'm going to generate some data. I'm going to generate that one. I'll explain it in just a second. These are the two I want us to focus on. Okay. So Y2. Okay. All right. So here's the firm right here. We'll start here, 1980. Let's get rid of some of this stuff. So we'll start with here. All right. So this is firm 1 in 1980. It's not going to be treated until 1986. All right. And I've got here a Y0, Y2, Y, right? All the same, right? So always the same here, this hypothetical stuff. And then in 1986, 1987, right? In 1986, firm 1 is treated and its treatment indicator goes from a 0 to a 1. Okay. Y0, 7.4, Y2, 17.4396, and Y, 17.4396. Okay. Right, 1987. Firm 1 in 1987, it is treated. It's already been treated. Its treatment indicators are 1. Y0, 8.6. Y2, 18.5. Looks like it only went up by 1. And then Y goes up by, well, that's a lot bigger. That's like an 11. Watch how these are different. Group not in here, 1988. This went up by right here. This goes from 8.6 to 9.14. This goes 18.57 to 19.1. Notice how these are just growing by 1, but these are getting bigger. This went from 6.6 to 17.4, went 17.4 to 28.5, 39, 50. Notice how it's getting bigger and bigger. Okay. So what I've done is I have generated 2 types of treatment effects. Y0 is basically the firm's outcome had no treatment ever occurred. Why 0? Start at your intercept, go up by n, add in the error term, where on average the error is 0. Okay. So on average, every firm, on average, every year, every treatment group, okay, on average, every treatment group would have grown by 1. Okay. So yeah, this is kind of growing by 1. That's what would have happened to everybody had nobody been treated. Here, this is the new realized outcome, Y2. And in the year that it's treated, 0 to 1, treatment effect, 10, 8, 6, 4, treatment effect, depending on your group, goes up by either 10, 8, 6, or 4. So look, Y2 is in this period right here, it's not treated. So those are the same. It gets treated. And now this goes from 7.4 to 17.4. This goes by 8.6 to 18.6. This goes 9.14 to 9.19. Okay. So that is our constant treatment effects. And it's this one. The 1986 group has a treatment effect of 10, and it's always a 10 in every single year. The 1992 group has a treatment effect of 8, and it's always an 8 in every single year. The 98 group has a treatment effect of 6, and it's always a 6 in every single year. And treatment in 04 group has a treatment effect of 4, and it's always got a 4 in every single year. And that's because mechanically we have a dummy variable equal to 0, 1 times TE, and TE is either a 10 if you're in group 1, an 8, 6, 4. Okay? Versus this situation. In 86 group, the 1986 group's treatment effect is a 10. You can see it. This is the baseline. This is the new realized outcome. 17.4 minus 7.4 is around a 10. In 87, 28.55 minus 8.6, 28.6 minus 8.6, that's a 20. In 88, says it should be a 30. 88, 39 minus 9, that's a 30. 50 minus 10, that's a 40. Okay, so this data generating process says take your intercept, so it says take your intercept 0.325, add an n 1 plus TE, which is okay, which is like here's a treatment effect of a 10 times a dummy variable, whether it's 0 or 1. If it's a 0, then all this stuff just gets canceled. And if it's not a 0, like right here, it goes 10 times year here minus treatment dates, that's a 0, plus a 1, that's a 1. So it becomes, you know, firm plus n plus 10 plus the error term. Second year becomes firm plus 8 plus 10 times a 1 here times how many years it's been since treated. So the more time that's passed, the treatment effects are getting bigger with this variable, staying the same with this variable. Treatment effect is always a 10 here, and here the treatment effect gets larger for all these guys. Okay? So those are two types of situations that are relevant for two-way fixed effects. First one is constant treatment effects. The second one is dynamic. Okay? Constant, dynamic. Now, we know We want to know this regression. Okay, we want to know that regression. We want to know if I regress outcome onto a dummy for whether you're what firm you are and a dummy for what year it is, and then I put in a treatment indicator, what will I find? All right. So let's just kind of look at this real quick. What even should I find? Let's take all these cells. Let's take the average. All right. So the average of all those numbers right there, the average of all those numbers is an 8. Okay. But OLS, because of its complex averaging, OLS, remember, is going to weight these up and it's going to weight these down. So when it does that, it actually is going to be a 7. So if I was just simply to go sum TE, the average of the treatment effects in the data is a 7. Okay. The average is a 7. So the average treatment effect is a 7, right? For constant treatment effects. So I'm going to run a regression here. I'm going to run a regression of, for the non-dynamic treatment effects, I'm going to run a regression. Here's a reg. Okay. Y2, year fixed effects, the absorb command here, A, comma, A, and you put in the panel identifier, ID. Okay, so I got year fixed effects, ID fixed effects, going to suppress suppress the actual presentation of it, but it's gonna still run it. This is like an old high dimensional method, and then take the dummy variable of treat 7. Okay, so we shouldn't be surprised because we know that 2A fixed effects will equal the variance weighted ATT, which is a 7, plus variance weighted parallel trends. And the thing is, I built parallel trends into it because look, had the treatment not occurred, okay, had the treatment never occurred, then every unit's potential outcome in a world where not treated would have grown by, start at the intercept and grow by N plus E. On average, N plus E is a 1 because on average, E is a 0. So it would have always grown by 1. Okay. Which is what that is. That's my potential outcome. That's my Y0 in a world we're not treated. So we know that if you do not have dynamic treatment effects, and this is the only thing that 2A fixed effects will identify. It'll equal the variance weighted ATT, which is a 7, plus variance weighted parallel trends, which is a 0, minus the change in ATT. And we know ATT is not changing. It's always 10 for a group. It's always 8 for a group. It's always 6. It's always 4. Okay. So let's run that regression again so we can see. Oh, and it's a 7. Just okay. So we're not surprised because it's as though that's 0. It's as though both of these are 0. Question is, what's going to happen here? See, because in this case right here, this data generating process, the treatment effects are getting larger. And as they get larger, I mean, the earlier treated groups, which this will be 86, 92, 98, they're all going to be earlier treated compared to something later. Their treatment effects are getting their ATT, the change in their ATT, not that, but the change in the ATT is getting subtracted. Okay. Even with parallel trends, you'll get the variance weighted ATT minus the change in ATT. All right. Well, so again, what even is the correct answer? All right. Well, let's average this up. Well, just the average of that is an 82. The average of that is an 82. That's not what the variance weighted ATT is going to be, because the variance weighted ATT is going to blow this one up and it's going to shrink that one. So I don't really have like a easy to express variance weighted ATT because I'd have to go through it. But it's definitely not a 7. right? It's definitely not a 7. It's going to be a big number, okay? So what we're going to do is we're going to run this. But the thing is, though, here's the thing we do know. We do know the treatment effects are always positive. That's the first thing. We know the treatment effects are always positive. We know the dynamics are positive. So the treatment effects start at positive numbers. They get bigger, okay? They get bigger over time. Their aggregation should be positive. But the problem is, whatever that variance weighted ATT is, and that's a 0, it's possible that if that's large enough, that number will not be positive, let alone be unbiased. Let's see if we get an 82. Negative 6.69. Now think about that. Think about that for a minute. These are these two variables, y2 and y. They both start out at an intercept. They both grow by 1 every year. They both have a law. They're both based on the same treatment indicator and the same base value. The only difference is this one never has dynamic treatment effects and this one does. And then notice the other thing, no covariates. It's not a single covariate in the data. It's not a single covariate in the data. And the error term is on average 0. It's the same error term. It's the same error term. And yet this is unbiased. And this isn't even the right sign. When you have two-way fixed effects, OLS will calculate a weighted average, a positively weighted average over of all diff and diffs in the data. But when you plug in the potential outcomes notation, you see that inside those diff and diffs are strange expressions. Okay. Inside one of those diff and diffs are strange expressions. Specifically, the good diff and diffs, the standard ones are ATT plus parallel trends bias. And the bad ones use already treated groups as comparisons. And they are ATT plus parallel trend bias minus the dynamically the change in ATT of the earlier treated group. Okay. And so what you realize is that it's the same thing we saw on Sunday. Simply using an already treated group introduces a bias. And the bias is on, where is the bias? It's on the dynamics of the treatment effect for the comparison group, and it's a negative weight on it. It's a -1 times those dynamics. So even if those dynamics are positive in every period and getting larger, the -1 multiplies by it, pulls it down. If these are large enough right here relative to this, even with parallel trends, it can still flip the sign. Clement and Chase Martin and DeHoefel, they call this, they say OLS does not have a no sign flip property. It does not have it. With differential timing. With differential timing, meaning multiple treatment groups at different periods, two-way fixed effects will estimate a weighted average over all possible diff and diffs. But that does not mean the sign will be the same sign as your treatment effects, because diff and diffs are not the same thing as the treatment effects. Diff and diffs are not the same thing as the treatment effects. And so it can be not just biased, it can have the wrong sign. Okay. So the truth was an 82, and I used two-way fixed effects, and I found a negative 6.69. Negative 6.69. Why? Because of extreme dynamics, and there is absolutely no way that you could have known that. There's absolutely no way you could have known that, because I have two variables here, y2 and y, and there's no way by looking at them, because these are realized outcomes and not potential outcomes, there's no way of looking at them and knowing whether you're looking at the data set for which there are no dynamics, or that there are. And this has nothing to do with the comparison group. Well, it has to do with the comparison group. It doesn't have anything to do with the comparison group not satisfying parallel trends. It's got to do with the comparison group being already treated. The parallel trends can hold and still be a bad control. Now, we know here that two-way fixed effects right there, this two-way fixed effects coefficient is equal to a weighted average of all of those. Here's the weights and here's the diff and diffs. It's equal to a weighted average over all of them. Well, we could just calculate those weights, calculate those diff and diffs, add them together. Yes, I sure can, Saban. I will absolutely do it. Well, I can't define post. That's a good question. Let me show you real quick, Saban, why. So real quick, what we're going to do is we're going to show, see, there are no never treated groups in our data. There are no never treated groups in our data. And so since there are no never treated groups in our data, all that we really have are the two-way fixed effects coefficient is just going to be a weighted average of this one and this one. And this is the early to late, and this is the late to early. Right? So I ran the regression, negative 6.69, and then I get that negative 6.69, and now I'm going to manually calculate each weight and each diff and diff. There's a command that'll do it called DD timing. So I did it, and I'm going to take that weighted average. So I'm going to type it in. Display 0.5 times 51.8 plus 0.5 times negative 65,180. Supposed to be that number and that number are identical, which would mean that since that number is negative 6.69, this should be negative 6.6, and it is negative 6.69. Okay. All right. So Saban asks, can I run a regression of reg Y onto treat post and I dot post I dot treat? Well, I don't have a post variable. Okay. So how do I generate a post variable? Generate post equal 0. Wait, let's start drop post. Generate post equal period. Yes, that's fine. Replace post equal 1 if year greater than treat date. Okay, hold on. Drop post. Gen post equals 0. Replace post equal 1 if year greater than equal to treat date. Tab post. Let me see if this will work. I actually haven't run this before, so I'm just curious. Post pound treat. Can't do it. I'll have to think about that, why that specification is not working. It will not do it. Post treat. I got to think about it. It's not letting me run it. Something about it doesn't work right. And I'll have to think about that. Why? Because I wasn't expecting you to ask me that question, David. But and my brain's a little melted. But the only way you can do it is reg, you go xi reg y I dot ID I dot year treat. It's gonna take a second when I do it this way. So many. So there's so many. Does it negative 6.69. Okay. But I'm gonna sit and think about it, saving. What if apologies have been stated as our year? Yeah, that'll, well, if they're not, if they're then you have differential timing, Madalena. So you've got individuals being treated at different points in time. So either you're gonna have to make a decision. In this case, you would have you know, I mean, it wouldn't correspond to the parameter estimate because you'd be coding some people as being treated when they're not. Because you'd say like everybody's treated in this year, but they're being treated at different times. So I guess that's probably true all the time. It's probably true all the time, but I need to you'll get some parameter estimate that is, well, they won't be doing. Let me think about that. I'm kind of wondering a little bit, but let me think about that, Madalena, and kind of get back to you. Well, it's more of a, I think Madalena is more describing like, do you end up with the same issue in the coefficient estimate if it just, you've got everybody being treated in 05 mechanic, but in reality they weren't. And I think that your number won't be right. That whatever you end up getting, it won't be correct. Because you're not doing the correct diff and diffs. But that doesn't mean that you're going to be using already treated groups as controls. So I'm not exactly sure how to think about that off the top of my head. It will be biased. That I'm positive of. It'll be biased, but I'm not sure exactly what to think of it, but I'll think about it. Oh yeah, this example is it's here. If you go to mixtape sessions here, lab, Baker. Sorry, I thought that was clear. It's here. And you have it all kind of like spelled out here. But in the solution, it's baker.do. So that is actually, and the DD timing, it comes from, it's here. You have to install it. DD timing. There's another one called bacon decomp, but You want the Excel? Oh, the Excel. Yeah, yeah. The Excel is also in the slides. Sorry. I thought you saw that. It's in the slides itself. I'm sorry. Gosh, I didn't even realize I didn't say that. It's right there. So, oh yes, thank you, Charlie. Gosh, exactly. Exactly. Thank you so much. No, no anticipation is not violated. Oh, for that one. Yeah, it would be Saban. That's right. For some of those, it would be violated. Yep. Do you notice how mine is not no anticipations built in? This is how you know you have no anticipate. This is no anticipation visually. No anticipation means in the pretreatment, it's not treated. There is no treatment effect if it's not treated. So here it's not treated, so there's no treatment effect. Here it's not treated, no treatment effect. All these are zeros. Okay, so that's like I have no anticipation. And when a unit gets treated, its neighbor does not get treated. Like we built into the data generating process, no anticipation to the parallel trends. Yeah. Gosh, thank you, Charlie. I literally was just like, I could not think straight at all. And I forgot treat was time varying. Ordinarily, treat is not time varying. Treat is a group identifier. So I would need more like XI reg, I'd have to use the treatment. I'd have to use the group identifier. So I'd be like group interacted with post or something, but I don't even think post is going to work either. But I need to think about that. Thank you. All right, I'm gonna answer these questions. We're gonna take a 15-minute break. So let's come back at 10, 17, 22. Come back at 22 minutes on the hour. We'll be right back. So I've been obsessed. So I wrote Angrist, and I said, trying to track down the origin of the phrase parallel trends. Here's what I can find. I mainly find Richard Blundell writing about econometrics of diff and diff in the 90s, kind of proselytizing it. He'll appeal to strict exogeneity. Hito and Susan have an 06 econometrica where they said it's too strong. So then I had 3 clues. Heckman, Ickemer, and Todd. It's the first time I can find them. I write it down. They write down that conditional parallel trends. They don't call it that. Then I found this old empirical handout that Esther DeFlo would give to the Harvard MIT students that were writing dissertations in development, labor, and public. That was 02. She uses parallel trends. She puts the word in parallel in quotes. And then Abity has this 2005 restud, which I found here. Readings. And he says it. Parallel paths. I think he says parallel trends. But all right, so that's 05, but it was accepted in 03 and it was submitted in 01, which the 01 puts it before DeFlo. So I wrote Abity, he hadn't written back. So then I was like, Abity and DeFlo were both Angrist students, the same cohort, pretty much like that late 90s. So I asked him, was Angrist the one that invented the phrase? So this is what he wrote. My 1999 chapter, Handbook of Labor, Economics with Alan Kruger. Diff and diff pitfalls. Like any other identification strategy, diff and diff is not guaranteed to identify the causal effect of interest. Meyer, 95, Campbell, 69. Outline a range of threats to the causal interpretation of diff and diff. The key identifying assumption is clearly that interaction terms are zero in the absence of the intervention. Interaction terms would be referring to it's not differential timing, it'd be this. The interaction terms are zero in the absence of treatment, meaning when in the absence of treatment, you could still do an interaction, You'd be doing it on Y0 though, and that better be a 0. So he says, in fact, it's easy to imagine it's easy to imagine that unemployment rates evolve differently across cities, regardless of shocks like the marital immigration. One way to test this is to compare trends, outcomes before and after the event of interest, or after. So he's kind of describing an event study. Blah, blah, blah. Identification of causal effects using city-year comparisons clearly turns on the assumption that the two sets of cities would have had the same employment trends had the boat lift not occurred. He's talking about the Mariel boat lift paper. But then he says there's this Meyer 1995 Journal of Business Economic Statistics article. I don't know if I have that in here. I'll find it and put it in there. Well, it's not really, it's about natural experiments. It's in he edited it. Oh, that's interesting. A second and underemphasized advantage of the long time series for outcome measures. Second underemphasized advantage of a long time series outcome measures is that they may allow the researcher to examine, he's talking about parallel trends, he's talking about pre-trends, if the treatment and control groups tend to move in parallel, that is, go up or down together. Huh. So it at least goes back to Meyer, and I'd have to get this Campbell thing, but it at least goes back to Meyer. Isn't that kind of cool? That's kind of interesting. So the phrase is probably not parallel trends. I need to do it again. So, all right. So here we go. Rowie says, I have another question. Oh, and oh gosh. Okay. So now it'll be a little fixed. And I updated the what's it called? Baker, the do file. All right. So then slides. Okay. So then let me get that. Let me get this. All right. And then we have another question. If the exact year of implementation is not clearly available, all right. Oh, I think it's gonna be tough, Rowie. I mean, I have a paper where I do have something like this. Um, I think like, okay, if you literally do not know the exact date of treatment, I would definitely not over stress your interpretation of the diff and diff coefficient. What I would probably do is this. I could have sworn I had saved that. Here's what we did. We have this paper in the Journal of Health Economics where we were looking at the effect of fracking. We were looking at the effect of fracking. I'll put this in the we're looking at the effect of fracking on the spread of STDs. And we were kind of linking it with seeing if it could be linked with sex work. So let me show you how we handled it, because it wasn't really clear exactly when fracking started. And so what we did instead was we just did event studies. We just did event studies, and because we don't know exactly when these things kind of can be clearly starting, we do event studies to just kind of show the evolution. And that might be probably a little bit safer. That might be a little bit safer. I mean, because if you're just going to run a regression, and you don't even know when it occurred, then probably just, set it to 2011, and then just, you could either do it for everybody or you could do it state by state. But I just would probably, I'm not exactly sure how I would write that up per se, but I would look to something like that as an inspiration of how to hedge a little bit and not overstate it. But you don't want to like say, I know it happened somewhere in this time. If you can pin it down, obviously try to get it as close as you can to the treatment date. But if you cannot, like it's literally impossible, then you're not going to be able to present anything as an average treated on the treated. You're going to have to probably convince people a little bit with those event studies and just show, yeah, there does appear to be, a growth. So long as you have states that did not get treated, though. That's really the fatal part. The fatal part is on both sides, getting the treatment right, getting the control right. Those are both important, but they're both critically important, but like they're a different kind of problem. So like if you're using an already treated group as a comparison, it's not going to be biased unless those underlying treatment effects are dynamic. That means, if you coded somebody up as a control group who was already treated, but in fact they were really never treated, it's not going to matter. That's not going to matter. That what's going to matter is the actual dynamics. That's what actually does it. All right. So in R, I use the diff and diff package. That's a good question. If you look at ooh, okay. So if you look at the here, diff and diff 2 lab Baker solutions, and you go to baker.r, okay, if you go to that right there, that will tell you what the command is in R. Hopefully this is not broken. I'm in big trouble. Maybe it's okay if we just kind of pause for a second and just take a break. Um, no, that's not it. Maybe that's not it either. Maybe I don't have I've got actually all of the, I've got all of the, I don't have the bacon decomposition in here. That's surprising. I thought that Fixest does have it. Let's see. Fixest bacon decomposition R. Is that where it is? There's a bacon command. The bacon decomp command. Okay, yeah. So it's the bacon decomp command. So you can do it. We might try to figure, oh, look, they're using my example. So you can do it using the bacon decomp package. I don't know who wrote this. But that's one way. So let me put this in chat. Okay. Could the staggered diff and diff be used in a situation where a panel gets treated at one or more time points in the sampling period, but become that Tockley, that is the turn on and off design, and that is for DID multiple GT. And it's called two-way fixed effects weights, DID multiple GPT. You so okay. Well, there's a lot of stuff in here I hadn't seen before. Um, oh, I hadn't seen that. So this allows for treatment switching. Units can move in and out of treatment status, time varying heterogeneous treatment effects. So it's one of the most flexible diff and diff estimators currently available. It was historically kind of slow, and now it is very fast. That was one of the things that Clement said here. Beta version, it's much faster. Okay, so I have it binary. So I gotta look at this, but apparently this is much faster. So they've been very good about making their stuff in Stata, and others have done it in R. So let's see. Okay, so I'm gonna go ahead and start back up. Sorry, I want to get started back up. Oh, they did. They posted like a week ago. The new one. Oh, okay, okay. Oh, the new paper. The new paper. Updated command. Got it. Okay. I wonder what that is though. Oh, it's their new one. Yeah, yeah, yeah. Their new RE stat. Okay. Yeah. If it's oh, and then there's this thing. Okay, yeah, sorry. All right. So let's get there is an R. Yeah, look, there is an R package for everything. There's an R and Stata package literally for everything now. So you go here to R, and here's all the R stuff, and there's a bacon decomp. Yeah, I should have known that. There's the bacon decomp there. And here it is right here. The AER one is DID multiple GPT. And that goes, I guess, goes with the Stata one. I don't, there's so many of these. I don't know I tend to like know the one I know and then not the others. But everything is now available in both commands is the good news in both packages. And Python's not listed up here, but many of these are in Python also. Okay. All right. So we now know two-way fixed effects is biased, right? Like we know it's biased. And so the question is, because we did it here and it was biased, and we know that when we do this, it doesn't give us the right answer. So negative 6.69, truth was an 82. So what's the deal? Well, two-way fixed effects is biased downward. And it's the bias is linear, so it can flip the sign in an extreme case. So it doesn't guarantee that it will. Even if it's biased, it doesn't mean that it'll flip the sign. But what I want to now show you is the Callaway-Santana estimator. So what we're looking at now is if you remember, it's like there were solutions for the differential timing scenario when you have heterogeneous treatment effects. Okay. And I was saying that it's basically like, you can break them up into two ways. Number one are these like what I'm calling 4 average and 3 subtraction style solutions. Okay. And that's going to be to Chase Martin and the hopeful. There's a bunch of them. Well, but the big one's 2020. Callaway-Santana. That's 2021. And then there's Sun and Abraham. Also 2021. And then you could even say stacking. Could even say stacking sort of is a version of this too, right? And then there is number 2, there's the imputation estimators or the outcome regression approaches. And that is Borsak et al. I think it's 2024. And then Gardner, 2-stage DID, which is unpublished. And then there's Wooldridge, Moonblock, which I think was published last year. And that's probably it. Okay. It's like there's basically these 2 solutions: 4 average, 3 subtraction, outcome regression. So what we're going to do is we're going to work on Callaway and Santana. We're going to work on Callaway, Santana, and Sun and Abraham. I do have prepped up to Chase Martin and DeHopeful, but for my own pedagogical success rate, let's put it that way, the Callaway-Santana, I've typically been able to help people get over the hump a lot easier with it and then move into the other estimators that have a little bit more complex notation after. Okay. So especially since we've already done the covariate stuff with doubly robust, it typically goes a little better if I do it this way. So we're going to do Callaway-Santana first, right? So when do you want to use Callaway-Santana? Well, you want to use it when you have to have differential timing. We have a differential timing situation. Okay, so what's that mean? Well, here's some examples. Do you think that you have treatment effects that will be different depending on when something was adopted, when a treatment was adopted, then it might be appropriate? Do you think the treatment effects are changing over time? And you have differential timing, then this is when it's appropriate. Do you think that the short run effects are different than the long run effects and that they differ by groups? Then it's another one. Do you think that the people that graduate during a recession might get different treatment effects than those that are graduating during an expansion? Then you might want to be looking at these solutions because why? What's the common thread? Heterogeneity. That's the common thread. You have a differential timing scenario, but you believe that there is heterogeneous treatment effects. Okay, so when that's the case, when you have heterogeneous treatment effects, and you've got dynamics or differences in groups by time, then you're going to want to move away from two-way fixed effects. And see, all of these are important because the nature of causal inference in this potential outcomes tradition is that the treatment effects are unknown. Nobody knows what they are. So, making strong statements about what treatment effects can and cannot be simply for the purpose of using a regression is probably not well advised. Okay, you would be better off if you really do not know the nature of the treatment effects, and I don't think anyone really does know, then it is not a good idea, in my opinion, to use the one estimator that places very severe restrictions on what those can be. Am I okay? Sebastian, I didn't know what you're talking about. So perhaps this would, because I didn't notice you were typing it. Are you talking about this slide? Yes. Oh, right, right. You could think about it as the responding more. Yes, you could think about it as the response more because it's basically about trying to figure out why the treatment effects might get larger over time or smaller over time. It can be any kind of situation where you believe though that those average tree on the treated treatment effects for the individual are changing as time progresses and that they might be different for different groups. Okay. In that situation, two-way fixed effects, that's two-way fixed effects specification that we laid out is not the right one. Right. So then what is the right one? Well, of those two that we were describing, the four averages, three subtractions, and the outcome regression approaches or the imputation approaches, of this, what we're talking about here with Callaway-Santana, what it's going to do is it's going to identify, literally what it's going to identify is each of these. It's going to literally calculate as many of these individual cells as it can. Okay? Each cell in that spreadsheet contains an average treatment effect for that group in that year, right? So this is the 1986 group. And the 1986 group in 1986, its average treatment effect is a 10. The 1986 group in 1995, though, is a 100. And the 1992 group in 95 is a 32. So you've got, something like in this scenario here, you've got literally 120 cells. Okay, you got 120 cells. So what each of these cells is called, it's called an ATT, all right, for that group in that time, or what's called the group time ATT. All right. That's not how it's calculated. That's not the estimator. That's just saying that's the target parameter. What Callaway-Santana is going to do, as well as the Chase Martin de Hopeful, as well as Sophie Sun and Sarah Abraham, what they're going to do is they're going to target these smaller level parameters, these group time parameters. And once it identifies, if you think about it for a minute, if you can successfully get all of these, right? Like let's say you could successfully get every one of those. You filled out a spreadsheet. Let's say you filled out a spreadsheet of every single one of those and you got them correctly. Well, then you could just average them. Okay, you can just average them. You got every one of them, add them together, divide. What would that number be? That 82. That 82 would be the simple average treat on the treated. So, you could essentially they're going to try to get the smaller ones first and then build up. But the question is, well, why would that fix the problem? Why would it fix the problem to go small first? And that's where the estimator is going to come in. The estimator is going to be successful at estimating. Like if you think back a little bit to this here, right? We had K squared diff and diffs, K to U, L to U, K to L, L to K, right? This one, untreated group, all we need parallel trends. This one, untreated group, all we need is parallel trends. This one, untreated group, all we need is parallel trends. Parallel trends, no anticipation, SUTVA embedded in it. This one, parallel trends is not enough. So you know what it's going to do? They're not going to calculate this one. That's the whole trick of all the new differential timing papers. All of them in some form or another, in some way, shape, or form or another, they will only attempt to calculate a diff and diff so long as they have a comparison group at that time period that is not treated. And if they do not have a comparison group that is not treated at that time period, they will not attempt it. Now, that is in some ways, that's trivial. The problem is doing that in such a way, where you can get an unbiased estimate, it still takes the econometrics. And so what Callaway Santana, and you can't just do it in a regression. Can't just do it, that regression will not do it. That regression, that coefficient with those fixed effects will always calculate all the diff and diffs and aggregate them. So you have to come up with an estimator that does it. You could do it manually. But exactly, yes, that's a perfect way of putting it, Anna. Anna says, so they get rid of the treated group as comparison bias, which I've never called it that, but that's right. That's exactly what they're doing. They're getting rid of the already treated group as a comparison bias. Okay. So let's look at how they're going to do it. And it's really not, the reason I like to start with Callaway Santana is because it makes it so clear how simple the solution is. Okay. So group time, average treated and treated, is the ATT for a specific group at a specific point in time. Okay, so it's for a specific group at a specific point in time. It is that cell. It's even that cell. It's just that cell is a zero. Okay, that cell, that cell, that cell, that cell, that cell. Okay. Group time, average treated and the treated estimates are simple diff and diffs. Simple differences in means, meaning simple diff and diffs. I should probably make that a little clearer. Simple DID weighted under Callaway Santana. So they're just simple weighted diff and diffs. They're simple diff and diffs, but they're gonna have weights in them. And when you do Callaway Santana or to Chase Martin or any of them, you no longer have to worry about heterogeneity. You don't have to worry about, with this one though, you also don't have to worry about heterogeneity with respect to the covariates, with respect to the timing group, or with respect to the evolution of the treatment effects. Callaway Santana, of all of them, Callaway Santana, it doesn't have any problems with any kind of heterogeneity. And they are going to allow us to choose our own aggregations. If you think about what OLS was doing, OLS was forcing the aggregation on us. Callaway Santana will allow us to do whatever aggregation we want to, because it's not going to do OLS in the same way anyway. It's not going to do it's not going to do the same kind of two-way fixed effects thing. So it's not going to have that variance of treatment bias. Okay. And then it's going to do a bootstrap for the variance. So I don't have to go over a lot of this because this is kind of stuff you already know. But let's talk about these two right here. We're going to have a dummy variable G with two G's in it. I'm using this from the paper. So we're going to have big G, lowercase g. Uppercase G is a dummy variable. It's a 0 or 1. Lowercase g means it refers to a particular group. Okay. So I'll show you what I mean in just a second. And C means that it is a dummy variable that says at that time period, there is a group that is there is somebody to compare it to. Okay. So you can kind of see here, even though Callaway Santana is going to attempt to get all this stuff, Callaway Santana is only going to be able to do it if in that particular period, I have somebody untreated. So let's say we're going to go after this one. I'm not going to tell you how we're going to do it yet, but let's say we're going to try to target and get that parameter. We want to get a number. We know the number's a 10. We're going to see if we can't get a 10. How do we do it? Well, we're going to use difference and differences. We're going to go 86 minus 85 for the 86 group. Okay. And we're going to compare it to groups of firms in 86 that are not treated, of which I have 750. The 92 groups aren't treated. The 98 and the 04 are not treated. So I'm going to calculate thereafter compared to there before. So I have what you can see here is that this spreadsheet's really nice because what it basically says is that it says So long as I've got zeros to the right of that cell, I can use Callaway-Santana on it. So I can get all of those because I have all of those as controls. I can get all of these because I have those as controls. Can't use it as a control now, but I can still use that one. I can get these because, I mean, I can't use these guys as controls because they're already treated, but for those years, I can get that one, but I can't get these because from 04 to 09, no one in my data set that I've been working with is untreated. The 92 group is already treated, the 98 group is already treated, and the 04 group is already treated. It works with 2-period diff and diff. Well, it works with if you have 2-period. No, if you, Saban, if you're working with 2-period diff and diff with covariates, that's the DR DID. Callaway-Santana though is basically connected to it. As you're going to see, it uses the DR DID formulas for incorporating covariates. But they're all like they're really not. Let me show you. They're not really complicated. Here's the 5 assumptions. Sampling is either panel or repeated cross section. Conditional parallel trends, meaning I've got a group of units in that period that are untreated, whose parallel trends with respect to X are the same as what would have been for my treatment group. Yes, Eduardo, I'm not sure I understand though. In the vignette package, we can include covariates that do not change in time. You're talking about Callaway-Santana, Eduardo? You're not talking about Chase Martin? Correct. That's right. It only is using the baseline covariates. If you're needing to use time varying covariates for some reason, Callaway-Santana will not accommodate time varying covariates, but other estimators will. So that will be the limitation of Callaway-Santana, is that it only uses baseline covariates. But the thing is, you have to remember the motivation for the covariates is essentially a form of matching in order to get your parallel trends assumptions to be believable. Okay. So the idea is that I'm trying to find a group of units who within those, whose covariates at that baseline do have a similar parallel trend as mine, as my treated group. But yes. All right. And so say it's a, all right, so I'm gonna come back to yours. Let's see. Get this done first. So then we have the other thing is they're gonna have irreversible treatment. So to Chase Martin and to Hopeful, they allow for reversible treatment. Treatment can be turning on and off. Callaway-Santana, irreversible treatment. Common support means that I've got units in the treatment group and the control group with the same values of X. Okay. That conditional parallel trends makes no statement about common support. It just is a statement. It's just a purely theoretical statement, but you're going to need common support with this in order to make an estimator. And then we have no treatment, we have no anticipation. Okay. Treatment effects are 0 pre-treatment, or treatment effects are 0 pre-treatment or at baseline, or simply that you're saying that the baseline is untreated. And here it is. Here is the inverse probability weighting. Yeah. Okay. This one. In the United States, Roe v. Wade's probably the only, and one of the Bill of Rights is probably the only Supreme Court case that anybody knows in the United States. 1973, the Constitution was amended. It says that in the paper, and it technically would just require using a different baseline is all. You can allow for anticipation. You're going to just need to change your baseline value. It's just a way of saying that, if you have anticipation. You're just going to need to find an earlier period where you don't have anticipation. So, it's just another way of reminding you that, you do have some options. The group time average treatment on the treated, it really is really robust to when your baseline is. So long as you've got a baseline that is untreated and all the other assumptions hold, then you'll always get an unbiased estimate, whether you use T-1 or T-10. It's just going to be a parallel trend assumption. The parallel trend assumption will always be with respect to whatever you chose as your baseline. So if you've got no anticipation is at the baseline and you choose, you go back far enough to where you're confident in it, that's going to also be where your parallel trend assumption starts. So it's just, they go together, but yes, no, it means the same thing. It's just a reminder that you've got to have, it's just a reminder that you've got to have the baseline correct. So here, Roe v. Wade, 1973, all of the United States gets constitutionally protected legalized abortion no matter where you live. And hold on. Just want to get the click here. Dobbs versus Jackson's Women's Health. Landmark decision. Court held that the Constitution does not confer a right to abortion. This was 2022. And so treatment turned on, turned off. Okay. That would be like the most, salient example to Americans, particularly since it just happened. But, so that would be an example. Okay. That would be an example of that. And, so something like that. So it turns on, it turns off. That I have my paper with Manisha Shah, legal, sex work was legalized or it formally recognized as legal de facto in 2003. And then in 2009, they recriminalized. So it went from criminal, legal, criminal, that kind of capital punishment. There was a previous time where it was legal. Then there was a moratorium that was put on it in the 70s where it was illegal. And then they allowed it to be legal again. And so you've got these kind of regime changes, these regime transitions that can happen. But Callaway Santana says, I'm only going to let you do it with the single absorbing state is what they often they'll call it, the going from 0 to 1 and then remaining 1. In fact, most of these estimators, if you look closely, that's what they're requiring. To Chase Martin is general in the sense that it allows for both. Okay. With some additional assumptions that have to be made about that switching. Okay. So here we have an estimator, the group time ATT estimator, right? Is this entire equation. It's an averaging. It's an average over all the stuff in the middle. Okay. And when you average all this stuff in the middle, you're going to get one of those cells. So these cells are the average treated on the treated. And this is an estimate of that average treated on the treated for that cell. And so it's going to be, and we're going to do this together right now. Okay. So we're going to do this together right now, rather than like walk you through it and like get you all stuck in this stuff. I'm going to manually code this. Okay. All right. So look what we're going to do. Number one, this right here, I will say this though. Let me do say this. So one way to just think of this is to just say that this is weight 1 and this is like weight 0. Whoops. Weight 0. And weight 1 is going to be the weight on the treatment units, the treatment DID, or the treatment first difference after minus before. And then W0 is going to be a weight on the comparison first difference after minus before. Okay. So all the stuff we're about to do, all the stuff that we're about to do is just about calculating weights. And then the rest of it is a simple difference in means. Okay. It's just a simple difference in mean. After, before, and there's the difference. So it's like I take an after minus before for the treatment group. That's one subtraction. I take an after minus before for the comparison group. That's a second subtraction. And then I difference those. That's a diff and diff. We're going to take weighted diff and diffs, where the weights are different for the treatment group than the comparison group. And this is the formula for the weights. Okay. And they're not bad. So watch what they are. All right. So look what we're going to do. First, we got to create dummies for which group you're in. So we have 4 groups. We're going to have 4 dummies. Okay. Secondly, I'm going to estimate a propensity score. Now I have no covariates in my data, right? I have no covariates in my data. My data never generated any covariates. So what am I going to do? What I'm going to do is you have to do this. This is the only way it works. So I'm going to run a logit of the dummy. Are you in group 1? If it is here. All right. So it's like, I'm going to use before everybody is treated. All right. So this is before everybody was treated. And I'm just going to say, what's the probability you're in the treatment group given covariates? But I'm only going to have one covariate. And that covariate is going to be basically a constant. It's going to be a constant. I'm going to regress G1. Oh, I forgot to do something. Hold on. Let me show you this. Okay, so I'm going to go list, state, treat, time till in 1 to 10. All right. List, state, treat, time till in 1 to 10. All right, so look. So I got to figure out how to tell Stata. I've got to figure out, I want to calculate a propensity score of the probability of being in group 1 given covariates when I have no covariates. And I know that, like, if I'm calculating that, estimating that parameter, I've got 250 firms that are treated. I've got 250 firms that are treated. I got 750 that are not treated. So if you look, tab G1, I've got 25% of my sample is treated, are in group 1, and then 75% are not treated, right? So what I do is I'm going to create a counter that says, how many years is it until you're treated? So in 1980, group 1 group 1 actually in 1980 is not yet treated. That's why it's got a 0, but it's actually 6 years before it's going to be treated. Okay. So I created this variable called year minus treatment date, time till year minus treatment date. And so I've got, like, basically, I know that if your time till variable is negative, you are technically not treated. Okay. So let's go down here. I run my propensity score, and I include in my propensity score 2 groups of people. Are you the treatment group, or are you not yet treated? Are you currently not treated in that time period? And I limit it to 1991, but I could have limited it to 85, 86. I just want to get in whatever this range is. The propensity score is going to always be the same for this period. When I get into this period, the propensity score is going to be different because I'm only going to be able to use this group as my treatment and these 2 groups as my control. So it's going to be like a propensity score that's just, I'm going to drop that group. So I've got to adjust. This is how all of these methods are a little bit different. They all have to kind of address the fact that they're kind of dealing with some sample selection as they kind of slice the data a little bit differently. And so it's gonna have to make some adjustments, and it's going to do that through this propensity score also. So we're going to have logit G1, predict PG1. All right. So I know tab G1 that there is a I know that there are 25% of my data in that year is in the treatment group. That means if I was to randomly pull out of the data, if I was to randomly go into 1991 and I would just randomly pull out a firm in 1991, there's a 25%, there's a 0.25 probability that I pull somebody from group one, right? So I ran a propensity score. I ran a logit and I got a propensity score. I regressed G1 onto a constant. Predicted PG, I predicted the propensity score. And everybody is equally likely to be in G1. Everyone is equally likely in 1991 to be in the treatment group because they all basically look like identical firms. And I didn't, don't have any covariates. So if you just randomly pull somebody out of the sample, it's the number of units in the treatment divided by the full sample. And that's 0.25. All right. So I've got now dummies for the numerator, and I got a propensity score of 0.25. So I'm not done with the numerator, but because I haven't gotten the numerator weight yet, but I got that part of it. Okay. Now what I'm going to do is I'm going to calculate my post-treatment and my pre-treatment, but I need to figure out which parameter am I going to go after. So what we're going to do is we're going to go after this one. We're going to go after the 1986 group time ATT, right? That's what we're going to get. We're going to go after the 1986 group time ATT, right? So to do that, I got to get a variable that says, well, what is your outcome in 1986? What is your outcome in 1985? G minus 1 refers to my group, my 1986 group, the year before, baseline. Since we're going after each of these individual cells one at a time, see, they each have their own baseline. So if we're going after 1986 group parameters, it's always going to be 1985 is going to be my baseline. But if I was going after the 92 ones, then 91 is going to be the baseline. 97 is going to be the baseline. And I can't even do any of these. So these I never can get any of those parameters. So the 04 group is just going to function as my comparison group, at all times. But it's the only comparison group for my 98 group. Okay. So we're going to do that here. 1986, 85, pull it out. So now what we've got is dummies, 0.25 propensity score, 86, a variable that's called, what is it called? Y post. So I got a variable called Y post equaling the value of the treatment, the value of the outcome in 1986 for everybody, not just the treatment group, and 1985 for everybody, not just the treatment group. Now I got to get these denominators. This denominator right here is sum G1. It's the mean of G1 in my data set. Well, the mean of G1 is a 0.25. But in Stata, you have to use thisegen command. So I'm going to go by sort year,egen. I'm going to generate a variable called G1 mean. So that's the G1 mean. And it's going to be the average of G1, which I already know is a 0.25. Then I've got an average of the inverse probability weight. This is the average of the inverse probability weight. This is basically the Abity. This is the Abity version that we did last Sunday. This is the Abity version of Callaway-Santana. Okay. So we're going to go here. We're going to take the average of this whole ratio. So notice, since we're taking an average here, right, but these aren't averaged, the numerator will be a number. It is the average inverse probability weight for the comparison group that you're using. And you have two different kinds of comparison groups, Sebastian. You could use a never treated unit, or you could use a not yet treated unit. Okay. You could use a not yet treated. We're using anyone at that time period that is not yet treated. And we don't have any never treated. So it's basically, for this one, we're going to use 92, 98, and 04, all of them, because all of them are coded at all of them. All of them all of them were not yet treated in that period. So we're using all three of those groups. You could use a never treated, but we're not doing it because we don't have any. Right. So we're going to take this average. But the thing that I'm wanting to bring to your attention is that the numerator is unique to every firm. The denominator is common. It's the same for every firm. Yeah. Yeah. So we're going to get that. Okay. So now I got this. All right. And now that I got that, we create the weights. We create the weights. So here's the weight. Weight 1. Okay. Weight 1. I'm going to make it right here. Weight 1. And weight 1 is going to be G1 over mean G1. That's going to be the weight on the treated units. And then this one here, weight 0, that's going to be propensity score over 1 minus propensity score divided by the average of the average of that entire IPW weight for the comparison group. There it is. That 1 minus G1, that's C. Okay. 1 minus G1, it's going to be propensity score divided by 1 minus propensity scores divided by the average. Yes. It still has to be done. It still has to be done for that reason. Well, this is what is this is required for this even sort of pieces of this showed up even in Abbedy's estimator, where you would have like, so there were pieces of this even, well, this is in Abbedy's estimator. The only thing that's new is this denominator part, but no, the weights are, there's only one target parameter, and that's the average treatment on the treated group time. Okay, so this is the group time ATT. I'm going to get to that, Lygia. That's what I'm going to get to. This is the group time ATT. And so the weights are going to be, oh, yes. Yes, Eduardo. What kind? Well, what kind? So the weights will be different for the different groups and the different time periods. So like right here, okay, all of these right here will have the same weight. Okay. But once I get into this range, the propensity score changes, because now rather than it being, a propensity score of 1 out of 4, it's going to be 1 out of 3 because I have to drop these people. So that means this numerator is going to change, and that means that mean is going to, that denominator is going to change. When I go into here, I want to get that one, it's going to be a propensity score of 0.5. 0.5 divided by 0.5 over the average of 0.5. Well, it won't, the weights, now, so the weights are not based on the dynamics. They're not based on the dynamics. The weights are purely on the diff and diff. This is just simply a weighting of the actual data. And that will depend, that weight will depend on, which group and time period you're focused on. There'll be blocks where they're the same, and then you'll move down. And if you lose a comparison group, suddenly the propensity score will no longer be calculated the same. It does it itself over and over again. But see, if you think back to how it's calculating the propensity score, it calculates the propensity score based on the year and which group you're talking about and how many units are not treated in that year. So all of a sudden, if you just lose a bunch of units, technically the propensity score will be different. And if the propensity score is different, then it'll change. And also, if there were covariates, it would be different because the baseline will be different. So the weights do change, but kind of in very predictable ways, very simple ways they change. Largely having to do with what's your baseline and what's your sample. That's really it. So now what we've got is we've got everything. So we've got weight 1, weight 0, post-treatment outcome, pre-treatment outcome, and an indicator for which group we're talking about. So let's calculate this. So we're going to calculate the first number, and that's going to be weight 1 times YT. Weight 1 times YT. Then I'm going to do weight 1 times YG minus 1, or Y pre. Then I'm going to do weight 0 times the post, and that's going to be weight 0 times the post. And then I'm going to have weight 0 times the pre. What do I have? I have now 4 averages. Remember what diff and diff is? 4 averages, 3 subtractions. And I now have weighted 4 averages. I took 4 averages and I weighted them. Or rather, I am about to take averages. I've got weighted observations, but I'm about to take averages. Okay. So I do it. I calculate now a simple diff and diff. Post minus pre for the treatment minus post minus pre for the control. Now, I know that the group time ATT is a 10, and that's what I found, a 10. Let's do it again. Let's get that one, a 20. Everything is the same except for right there. That's the only thing that's different. That's a dummy. That's the average of that. Propensity score is not changed. Post-treatment is going to be different, but baseline is the same. See, here's where Callaway-Santana is really needing you to be sure that you have an untreated baseline. See right there, that right there is where you could get into trouble. You can get into trouble right there. So you've got to make sure that your no anticipation is holding, because Callaway-Santana only uses one period as its baseline. Doesn't matter how many pre-treatment years you have, Callaway-Santana uses one of them for the diff and diff. It'll use the others to calculate event studies, but it's only going to do it for that diff and diff. So that better not be treated. All right, so we do it again. Run through the whole thing. Should be a 20. It's a 20. And it's going to go on and do it. We can do it again. We can go to be the 30. All right, I did it for an 88. On and on and on. 30. I encourage you to do this yourself, but here's the magic. All that Callaway-Santana is doing, literally, all that it is doing is it is calculating every feasible diff and diff, which means it is getting all of these. It needs one baseline. Okay. It's getting all of these, of which there are 69 of them. It can't get any of these because it doesn't have a control group for these. This is the control group. Okay. No, it's YG minus 1. The reason it's YG minus 1 is that the G refers to the group treatment date. Okay, so it's like, that's G right there, 1986. So if you're wanting to get the 1986 parameter for a given year, you have to choose your baseline. What's your baseline going to be? 1985. G minus 1. You can't say T minus 1. You can't say T minus 1 because these are all kind of relative to a group. So you have to say they're going to have because they're going to have different baselines. You know, the baseline, the group time, the baseline for this one is not going to be the same as that one. Does that make sense? Y'all both asked the same question at the same time. But here's the great thing. So it's calculating every one of them. It's calculating every one of them. Exactly. Their groups are defined in terms of time. Yes. You belong to the 86 group. I mean, Tack, you're going to graduate from, I'm assuming like a doctorate, or you already have one. You've got some, graduation cohort that you belong to. And all the cohorts are grouped together. They're all grouped together. They belong to the same group. A group is a treatment date. That's what your common group is. Your common group is not your covariates. Your common group is your treatment date. And you're going to calculate average treated on the treated for a group. Yeah. Yeah. You could always have a different baseline. How you coded it up would be another matter, but like you could always choose G-2 or G-3. You want to choose, I mean, look, what drives your choice really? If it's not G-1 and it's G-2 or G-3, the only reason I can think of why you would do that is assumption 5 and assumption 2. Because those are the only ones that have to do with baseline. So you would be making your choice by where do I think parallel trends holds? Okay. And where do I think I have no anticipation? And you want them both to be the same. So whatever you're doing, you just want to make sure that you're doing that. Okay. But nobody's going to want to, so you can't get all of them. You can't get all of them, right? Because you can't get anything from 04 to 09. You cannot get anything from 04 to 09 because you don't have a control group. You don't have a control group from 04 to 09 for the 86 group because look, the 86 group, everybody's treated. You have no zeros to the right. Everybody's treated. So we don't even, so Callaway-Santana doesn't even attempt it. Callaway-Santana doesn't attempt it because Callaway-Santana, under these 5 assumptions, it can't do it. The only way you could ever use an already treated group as a control, think about it. The only way that you can ever use an already treated group as a control is if there are no dynamic treatment effects. If you are unwilling to make that assumption, then none of these can be calculated. Do I get something like 09, 04? You can't get it. You can only attempt, it is only allowed, Eduardo, to attempt 04 to 09 if you are willing to say that none of the comparison groups have changing treatment effects. They're already treated. See, they're already treated. So if you were to use these people as your controls, well, they will be violated because they have changing treatment effects. If you had a 2010, yes, it would work. Exactly, Amy. If you had a group of units that were never treated, all of these could be calculated. But we don't. All right, Eduardo said like the ATT for group treated in 09, but in 04. I'm not sure I follow, Eduardo. Like the ATT for group treated in 09, but in 04. Do I get something? I'm not sure I follow. I'm not following. But yes, Amy, if you have another group, like, see, this is the whole thing. If I had a 5th group, okay, call it the control, then I could do it. I could get all of these because I'd use him as a control. I'd use him as a control, him as a control, him as a control. Then you could do it. But I don't have it in my data set. Yeah. Yeah. I'm glad you like it. Yeah, I found it to be so helpful to just visualize. I mean, I'm a kid that grew up with spreadsheets, so I have to see this stuff. It's very, very helpful. Yeah, each series has a deterministic formula. But what are you saying, Ronald? I'm not sure I follow. When I run this in R, I get results for periods -1, -2, -3. When you run what in R? Oh, you can get results for any of these. You can get all of these. You can calculate this. You can calculate that one because you've got an untreated unit. You can calculate this one because you have a untreated unit. You can do all of these too. Okay. So you're the group time ATT, it literally is really simple. It's just a simple calculation, and you're only using this weight right here to determine if you're going to allow that unit to be used as a comparison group. Well, you could back out the issue is the example. Eduardo, I'm not following all the things you're saying, but you're saying, hold on, let me look at Ronald. Not sure, but couldn't you back out the formula to make a new control? As long as you have, Ronald, as long as you have somebody untreated, truly untreated, it's not really the formula. It's not really the formula. It's do I have somebody, this Callaway Santana, do I have somebody that at that moment is untreated? That's what drives the whole thing. Okay. That's what drives the whole thing. So if you have somebody that's like, so, you could like, so wait, does CS ignore the period? There is no control group. Yes. Well, it's supposed to, Tack. It's supposed to. It's yes. Callaway and Santana, the econometric estimator published in the article, the formulas for them ignore, as you say it, they ignore any calculation that is not feasible. They do not attempt any calculation that is not feasible. And what makes it not feasible is if there is no control group in that time period. Okay. Now, if you code it up yourself, you can make a mistake. And when you make the mistake, you might inadvertently, without meaning to, use an already treated group as a control. But Callaway Santana, as an estimator, will not let you do it. And so, we had a way of doing it. Our way of doing it in this analysis, this fake analysis, or this manual way, was right here. That's how we guaranteed that we did not use, in my stated code, this is how we guaranteed that we did not use an already treated group as a control. We put in time till was negative. And so what we did was we said, well, I'm going to run a regression of a dummy onto being in the treatment. Like I could do it like this. G2, and we'll just call it like, whoop. Okay. So if I did that, if I did logit G2, I'll do it like this. We'll still do G1, right? We'll still do G1, right? But now we're doing it year 2001, time till negative. Well, if it's 2001, okay, if it's 2001, then what's the probability? What is even the sample? What is the sample of units that in 2001 are either in the 1986 group or are not yet treated? It's this group and that group. So if I run this regression, okay, oh, it didn't even do it. So I didn't do something right. I have to play around with it. So I'm doing stuff off the top of my head. So something about that is not identified. So I'll look at this. But anyway, point is, Callaway Santana is not using already treated group as a control. And you just got to make sure that you're confident about the package that it is doing that. And so one of the things that's helpful to make sure that it's doing it right is to kind of have as your ground truth, I mean, you're not gonna have to worry about all this. All the packages work right, so you don't have to worry about it. But in a world where you had some new software language that you were trying to get everything coded up in something that nobody's done before, I would recommend working with a spreadsheet where you know the facts and just see if it gets it right. Okay. Can I calculate the AT on that screw is true enough for? I don't think you can. If there's a way to do it, then I'm gonna be blown away. Is there a way to do it? Oh, well, this is different, right? This is their paper. Okay, this is not my data. If you do not have an already treated group as a control, if you do not have anybody, here's some. Oh, okay. So you were doing that. Is this my data? Oh, it is my data. Okay. No, no, no. This is their data. County. I'll look at this, Eduardo. I'll look at this. If you can keep asking it, but the answer it roughly is that Callaway and Santana will not allow you to use an already treated group as a control because if there are any dynamics, it doesn't matter. It doesn't matter what you're doing. If there are dynamics and you calculate a diff and diff, it will be biased. We saw it at the beginning of Sunday. We saw it at the beginning of Sunday where we worked through it and it was like that's what it will always attenuate it down. Okay. But you're not going to want to, sorry, I'm jumping around like this. You're not going to want to obviously go through manually and calculate every single group time ATT. I did it here. I did it here manually, but you don't want to do that. So what do you want to do? Um, well, yes, kind of, Amy. Amy, let me show you real quick the command in R. Okay, let me show you the command in R. Um, and then we will look at it in Stata. Okay, so let me show you the command in R. All right, this is where is this located? This is in Causal Inference 2 Lab Baker Solutions, and it's bakercs.r. Okay, now I'm going to pull in here a packet. The package is DID. Okay. Package is DID. This is incredible. Pedro is so fun. I mean, Pedro is not afraid to write an R package and name it difference and differences. And now it is like the branded difference and differences package in R. Um, that was pretty smart. ggplot2 Haven. So Haven is going to allow me to pull in the Baker data set. And the first thing you have to do when you're working with DID is if you have anybody whose treatment date is not that is never treated, if you have somebody that's never treated, their treatment date will have a bunch of NAs. It'll be missing. So you have to change it to a 0 for DID. You got to read the documentation on all of these super closely. You have to read the documentation on all these really closely, and many of them will require that you somehow change the treatment date from missing to something that Callaway Santana will, or something that the authors of the package tell you to change it to. Callaway Santana says if you have never treated units, change the treatment date variable to a 0. Now, since no one was treated in the year 0, Callaway Santana know that a 0 is to be used as a comparison group. Okay. All right. So I do that. Did that. It doesn't do anything in my data because everybody was treated in my data, but this was treatment date out of the Baker data set. So I got that $ variable in that data set. And if that variable is NA, change it to a 0, change it back. It didn't make any changes, but had it not been treated, or had it never gotten a treatment date, that would have been missing and it would have made a change. All right, so here we go. So the command is attgt. right? So there it is, ATTGT. We have to put in our outcome name, our time indicator, our panel identifier, if it is panel, our group name, which is treat date, any covariates, the name of the data set, if it is or is not a panel. Are you going to allow an unbalanced panel? What is going to be your control group? Never treated or not yet treated? Are you going to, is there going to be no anticipation? Weights name. All right. So here. So I'm going to run it. So watch what happens over here. All right. So it ran it. Look what it did. It made an object called ATTs, the plural. It's the plural. I have now got a bunch of ATTs where this is an ATT. So I have all of them. I have all of them. I have, you know, I literally have all of these. I should have 69 of them. 69. There it is. ATT, 69 of them. And it looks like they have a bunch of numbers. Okay. Looks like they have a bunch of numbers, and I could display them, but I'm not going to do that. But there they are right there. There they are in there. You can see them showing up. Okay. Negative 0548. Negative 0548. Okay. So there's something in there that I'm going to be referring to, and they're going to be each of these individual. They just calculated every one of them. All right. But the question is, you know, you're going to want to present, you're not going to want to present in a study all of this ever. You're going to want to use it in some way that is reasonable. Okay. So what is that going to be? Well, what I'm going to do is I'm going to aggregate it. So if I've now got this, all right, if I've got these actual post-treatment ATTs, okay, I'd like to average them. That's one thing I could do. I could average them. The average, it's called a simple average. Simple average is a 68.33. Okay, it's 68.33. There it is right there. All I'm going to do is I'm going to average all of my group time ATTs. I'm not going to average these zeros. I'm going to average the post. So I'm going to type in simple. I'm going to take my command here. It's called agte. Say what kind of group it is, what kind of type, and I'm going to aggregate. So aggregate it, and I'm going to create an object called ag effects. There it is, 68.3. Makes a nice little table. 68.3, standard error 5, 95% confidence intervals to go from 58 to 78. Well, that's one thing I could do. And note, okay, so look, so it did it. It did it. It got a 68.3, and that is actually the correct number. That's the simple average. I could also, though, do, I mean, but if you think about it, if you've got all of those numbers, you could summarize, that's what they call it, summarizing. You could summarize them in other ways. Like this. I could take the average just of the 86 group. I could take the average just of the 92 group, which is a 52. I could take the average just of the 21 of the 98 group, which is a 21. Then I could average those, which is a 56. It's the same treatment effects, but the weights are different. In this example right here, the weights are different because what it is that this is using a 1/3, a 1/3, a 1/3 weight. But then that number right there is using a 1/18 weight. And this one's using a 1/12 weight. And this is using 1/6 weight. So it's using like these kind of slightly more complicated weights, but they have an easy enough to explain interpretation. So what I would do is I would say ag effects, ag TE, use the ATTS. It needs to use this thing. But instead of saying simple, say group. I'm gonna rename it. 56. Not just that, though. Look, 56, 56, which is the average over 95, 52, 21. And it's also got a 95, a 52, and a 21. Okay. So you have here all of those, and we're not done. If you've got, and I can also list all of them, here they all are. If for some horrible reason you wanted to do it, you could do it. You could list all of them. So in fact, like when I wrote this out like this, I got it from here, 10.0258, 10.0258. I just copied it. I just copied this down and put it in an Excel spreadsheet to show you guys. Okay. But look, pre-treatment, I even have those. I even have pre-treatment group time ATTs. I've estimated the zeros. Well, if you've estimated the zero, why do we care about the zeros? Why do we care about pre-treatment coefficients on things that are not part of the question for the event studies? So we can aggregate into event studies. Plot the group time ATTs. So look, let's see. All right, so that right there, 86 for the 86 group, that's going to be here. That's a 10. That's a 10, 20, 30, 40. It's a slope of 10. See how that's slope of 10? It's basically just plotting each of these with its confidence interval. Because this data has like no noise in it at all, the confidence intervals are like, they're not visible. They're there though, but you can't see them. Okay. So then you've got the first group, but look, it only goes to 03. Why? Because it did not attempt anything in the gray zone. So it only stopped at 03, 180, 180. Then we go down here to 92. We got all these zeros, 8, 16, 24. We did that. But we also made event studies. We made event studies for each individual group. And what this is going to allow you to do, is to check. This is going to let you check each of the groups' parallel trends, the pre-trends anyway. It's going to let you check whether or not, because maybe this is the case. Maybe the 1986 group does not really have very good pre-trends, but that does not mean the 92 group won't. That doesn't mean the 98 group won't. You have the ability with Callaway Santana, Son and Abraham, really all of them. You have the ability with these new ones to not just get unbiased estimates of the average treated on the treated. You also have the ability, maybe even for the first time on any project you've ever worked on, to really dig deep and explore the heterogeneity. Because you have literally calculated every single one of these parameters and they're unbiased, you have the ability to really go a lot deeper and try to figure out, well, is there something, was the early adopters different than the late adopters? Were the early adopters, do they satisfy parallel trends? There's a lot more scrutiny that you're allowed to bring to it that is kind of being like not possible with this like one coefficient that you get. This like just run a regression, get a coefficient, and then all the focus is on the robustness of the coefficient. Now you can explore the heterogeneity of the treatment effects by group, by timing group, not just by covariates, but by timing group. And I think that's new. I think that's new. Okay. But now let's look at Stata. Really straightforward. You're going to have to use CSDID, DRDID, but here's the command. It's called CSDID. And here, by the way, I will make a suggestion real quick. If you are going to use diff and diff in your project, and this is my nudge, okay? I would encourage you to cite the author of the package, okay? And the reason is for a lot of reasons. First of all, it was incredible that these people, it was incredible that Fernando Riaz Avila, it was amazing that he stepped in. I uh I think that this is true. I'm actually positive that this is true. It was I don't remember exactly when this happened, but originally the econometricians were really sorting into which package they were making. And so Brant Calloway is essentially, Brant is like he actually has a computer science major in college. And so he writes very good. He doesn't write just very good code. That's one thing to write good code. It's another thing to write software, and that's kind of what this stuff is more of. This stuff is more like software than writing good code. That this is flexible for all the users. And that's a big limitation because nobody cites the packages. They cite the papers. So Brant and Pedro wrote this. They wrote DID, the package, and there was no stata, and vice versa. The Chase Martin didn't have an R package. And so I was telling Pedro, and this is when I was on Twitter, I was telling Pedro and others, and this is probably like 2019, maybe it was even 2018. I really think that people need to write the code in Stata. I was getting really kind of frustrated. It's none of my business, but like I was kind of like going, nobody's good. I knew my age, people my age who are like 50, they're not gonna learn, like they kind of are dead set in their ways. They don't, many people my age, they don't know R and they don't want to learn it. And so it was like but given how popular Diff and Diff was, I could tell that it was creating some issues and panics and all this stuff because I was doing all these workshops. So I raised money and like created this like bounty, and I was like the first one to make Stata package will get $1,000 because I got my department chair put it up, and like nobody of these econometricians wanted to do it. And then the moment I did that, this guy Nick Huntington Klein came up and he said he would do it. Well, once they saw Nick do it, then they all did it. And so like Fernando did it. Asjad Nakvi does it. He comes in and does it. And then you just start seeing all of it. You just start seeing everybody begins to create these things. Okay. So CSDI, so what I would recommend you do is if you do use it, I would recommend that you cite their working papers. Many of them have published in R journals or in Stata journals, Journal of Statistical Software or something like that. I would encourage you to do it because it's a nice way. It's a nice way to give it. Well, first of all, it's good, I think, to let people know that you're using a reliable package, and it also gives them a site. So here we go. So you're going to go CSDID, outcome, panel identifier, year, okay, for the thing. And then you say the treatment date. You just say which of the, then you're going to look in the help file, but I'm going to use the IPW. Now watch. No never treated observations found. Watch what it does when it hits. When it hits it's going through right now and it's calculating all of these, but it's going to hit 04 and watch what it does. 04, 05, 06, 07, 08, 09, start over. Does it? This is the 92 group. 04, 05, 06, 07, 08, 09, starts over. And then what was that last one? That was the 04. And it does not even attempt any of the 04. That's 1980, 81, 82, so forth. Okay. So then it does it. Look. So what has it got? Here we go. It calculated all of the group time, average treat on the treated. It used as its outcome model regression adjustment. I'm not sure why it's saying that because I told it to use inverse probability weighting. So I need to dig into that. But anyway, so it goes 10, 20, 30, 40. It's getting all of them. Does not attempt the last one. It's telling you here what it's using as it's the 86 group, and it's telling you here what the baseline is. Okay, so then 92, 8, 16, 24, 32. It's getting all of it. And then it didn't even attempt it. Okay. Now I'm going to do a simple ATT. And remember, the simple ATT is 68. 68.34. But now let's do the group. And remember, group is 95, 52, 21. Group average, treated and the treated 56 or whatever it was. 56. That's the average. Some of the labeling's a little bit different, but it's still 95, 52, 21. And if you want to get the event study plots, you can get it. I'm not positive that's going to do it, but let me see. Yeah. Well, this is doing something different. I'm saving that for tomorrow. But you can go through and you can do these. You can do these here. Let me see if that does it. Yeah. Okay. So I have to spend a little time. So, but there's a way to make that plot also. Okay. So let me look here. All right. So these longer questions, I'm gonna type out my answer, Amy and Eduardo. I'm gonna try to study your question too. Germany said, could you know why they use short lags? Short lags? Why do they use a single period? Is that what you mean, German? Why do we use one single baseline? If that is what you're asking, from the output. Oh, yeah. Okay. I didn't know if you wanted me to get it. You mean this, right? You mean this stuff right here? Compared to right. So I do not know. I do not know why this is being done. I have eavesdropped on Andrew Baker and Pedro Santana talk about this in my Slack channel. So I have this Slack channel right here that's with them, and I've listened to them talk about it. For some reason, people are coding up a rolling baseline for the leads. So right here, for all of the post-treatment coefficients, they all use G-1, which means they use 1985. For the 92 group, they use 91. For 98, they're using 97. For reasons I have been meaning to just sit down and ask, what are you guys talking about? They are not doing that for the pre-treatment coefficients. They're just calculating simple differences in trends using a rolling baseline. And the reason appears to be so that they can get a coefficient for every single year. So they're going to get a 1984 coefficient by do they get an 85? Oh, so they still don't get an 85. They never get an 85 coefficient. So I don't even really know what's going on. So Here they just use 84 compared to 85. Here they use 83 compared to 84, 82 to 83, 81 to 82, 80 to 81. Or maybe it's 81 to 80. Yeah, that would be it, actually. No. Yeah. So that's right. So they go, so for this, they go 85 is the baseline, 84 is the baseline in order to get an 85 coefficient. 83 is the baseline in order to get an 84 coefficient. They basically do everything up to that, and I do not know why. I do not know why this is done. I was not planning on covering the unbalanced panel rock, but it will come up probably, so I can just sort of discuss it in the context of the Callaway Santana. I will kind of discuss. We're not working with. Yeah, I can make a note to myself to just mention unbalanced, discuss any issues with unbalanced panels. Okay, so I'll make a note to myself. Okay. I will. We're gonna do that at the end of the day tomorrow. MK, we're gonna do that at the end of the day. We're gonna talk about which of the estimators to choose or do all of them. I'm gonna actually give you code that will do all of them. Okay, I'm gonna give you code that will do all of them so that you can at least, if you wanted to do all of them, you could. All right. And I'm not gonna tell you which ones to choose though. I'm just gonna explain, you know, the most salient reasons that they're different. You're gonna ultimately have to make your own decision. You're gonna have to make your own decision about that. And then the typical output, I will be giving you two papers. We're going to discuss two papers about that. Yeah, yeah, exactly. So I'm going to kind of I'm going to talk about that there. This is where we'll talk about it tomorrow. Yes. Yeah, say it. I'm going to, because it's after 5, I'm going to have to read your question and respond. Okay. So I'm gonna start reading your question and try to give a reaction. But I want to go ahead and go ahead and get off now just because I have spoken so much. I know people are already filtering off. So I'll see you guys in the morning, and I'll post this as soon as possible. I know that was a long day, but I will see you guys tomorrow, and we'll start bright and early. All right. See ya.